So welcome to this tutorial on an introduction to CP Optimizer for scheduling. As I said, I will speak mostly on scheduling and optimization, not too much about CP. And there are many reasons for that, and you will discover them later on. So the first thing I want to say is a bit to give you a context of CP Optimizer, what it is. So in fact, it's a tool that historically is developed since 2007 by iLog, which is now IBM. And it's a descendant of iLog solver and scheduler. I don't know if you have heard about these tools. They were developed in the beginning of 2000 and 90s. So this is to say that our team at iLog has a big experience in designing combinatorial optimization systems and especially applying them to real-world problems, real-world optimization problems, okay? And particularly scheduling problems. So what does it mean, scheduling problems? Scheduling problems compared to more academical ones have several characteristics. First, usually they are large, sometimes very large. For instance, we solved at some point a scheduling problem with 1 million tasks, okay? A real problem from a customer with 1 million tasks, just in one shot, in the same model, using CP Optimizer. So the models can be large. Well, this is by no means saying that all models are that large. Of course, we have smaller problems, but quite often we have large models. The constraints are complex. You may have quite complex activities, quite complex type of resources to handle. And compared to many academical scheduling problems, the cost functions you want to optimize are also very complex. And usually you do not meet any problem with just minimizing the max plan, or it is very seldom. Okay? There are another interesting things when you work in an industrial context and want to provide some tools for doing combinatorial optimization in industrial context, is that you are working with tight deadlines in general for building the application, for building your model. You start from completely ill-defined problems because, well, it's never the case where you go to a customer and you say, okay, I've written on a sheet of paper the mathematical description of my problem, please solve it. It never works so. You have to discuss with them, they don't know even themselves their problem. So you have to deal with ill-defined problems, with moving targets, because at some point in the project they want to focus on some aspect, but maybe after they discover that, oh no, we better want to optimize another part, which is more important, or this is more important than what we initially expected. So you have moving targets. You of course have bad data, and it's difficult. Accessing to data and having good data is something very difficult. And of course you have a need for performance, because sometimes you are working in not real time, I would say, but you need an answer, a solution in, let's say, 5-10 seconds. Okay, so this is very challenging. So during these years, since about more than 20 years, we have been developing generic optimization system and framework. And with CP Optimizer, what we try to do, because we discovered that with the old generation of tools, they were getting too complex, and people were not able to use it. For instance, iLog scheduler's documentation was about 1,000 pages big. Okay, so you had to understand all these different concepts in order to be able to design a model. And then, once you had designed a model, you had to write your own search algorithm to solve it. So that was very, very difficult. So when we started with CP Optimizer in 2007, we decided to build CP Optimizer with one main objective. It is to lower the barrier to entry for solving efficiently scheduling and complex scheduling problems. Okay. So we will see what it means and how we hope that we have kind of achieved this objective. But this is just to describe the context a little bit. Okay, now what I will do in this preamble is maybe in order to know a little bit what you're interested in and what is your background, just to ask a few questions and to make a small poll in the audience. First, have you ever heard about CP Optimizer? Who have ever heard about CP Optimizer before? Okay, so some, not everybody. That's nice. It's an introduction, so it's.
It comes back.
Okay, that's fine. It come back. So it's an introduction. So, of course, if you don't know CP Optimizer, that's very fine. You would learn at least what it is, and if you know it, probably will learn some things, because what it is, it's an introduction, but it's quite a complete overview of the system. So you will have maybe a more global view of what it is. Who is familiar with constraint programming? Oh, okay, many problems. So this will be difficult for you, because the first thing you should try is to forget everything about CP for a while, at least for 2 hours. I'll be back on CP in the end of the talk, when I will explain mainly how CP Optimizer works under the hood. But in the meantime, try to switch off your neurons that speak about CP. Okay, you do not need it for now. Same question with mathematical programming, for instance, MIP or. Okay, so this is good, because if you know MIP, you will find CP Optimizer very easy, because it's the same philosophy. Same question for meta heuristics. I don't know, local search, genetic algorithms. Okay, good. And planning systems, or do you have? Okay, so most of the people here know the main techniques for that actually we are dealing with inside CP Optimizer. Not planning system. I will speak a little bit from time to time about the connection to planning, but CP Optimizer is mostly about scheduling. Okay, so you're given an envelope of actions to work with. Okay, but we will see some interesting connection with planning at some points. Okay. So what I will start with is just a very introductory problem. Okay, I'll describe this scheduling problem, and then we will see. I will show you at some point the CP Optimizer model for solving this problem. So actually, it comes from a real problem, but it's a very simplified version of the actual problem. This is an actual problem that we are currently working on with a customer. So it happens in the semiconductor industry, and if you want a description of the problem, you can have a quite complete description in this paper, in this recent paper. So, what it is about? Technically, in terms of scheduling, it looks like a flexible job scheduling with parallel batching. So, if we enter more in details of the problem, what it is? You have a set of wafers or some kind of disk of silicons to be treated by the machine, by some machines, and these wafers are initially grouped in some lots. Okay, so here you have, for instance, one lot with a set of wafers. Okay, each lot is associated with a size, which is the number of wafers in the lot. It has some priority, because some lots are very priority, they should be treated as soon as possible. You have a release date, they are not available in the entry of the shop before this date, and you have some due date. Well, this is quite classical. When you're looking at a particular job, the particular job had to follow a set of steps in the shop. Okay, so let's focus on lot 1 here. It first go on an activity in step 1, then later on, this is a precedence constraint, to step 2, and so on. Okay, so we have a chain of steps for each lot. Now, each step has to be scheduled on one machine. Okay, and you have a set of possible machines in your shop, in your workshop. So, for a given step, I should say that the step belongs to different family. Here, the family is represented by the color. Okay, so here you have the yellow family. Step 1 is a family, yellow family, step 2 is green family. So you are given a set of machine, and a given machine can treat only certain families. Okay? So here I give an example of two machines. You have machine M1. It can process either the yellow steps or the green steps. Okay? And you have a machine M2. It can process the yellow step and the blue ones. But you have a duration that depends on the machine. Okay? So, for instance, if you have step 1 is yellow, it could be processed by M1 or M2, but the duration would depend on the machines. And this is really important because in this industry, they have some really very, I should say that the machines are very different. So you have machines that are very dedicated to some work and they can do something very fast. You have machines where the job will take very long. So this duration heavily depends on the machine. Okay. I forgot to say, if you have any question, just interrupt me. No problem. Now, let's keep on. Interesting thing is that the machine is not a unary machine. It can process several steps at the same time. Okay? Because what happens is that in the machine, you can think of it as an oven, for instance. You can put several steps inside and treat them together. Okay? This is what we call a batch. This is in scheduling what generally is called a batch. So you see, for instance, that here on machine M2, it can process both the yellow and the blue steps. We have done a batch with these two lots, okay, and then a batch with these two lots. You can batch together only steps from the same family, so steps of the same color here. Furthermore, so when you batch together two steps, they start and end at the same time because you put them together in the machine, you treat them, and then you take them out. But the machine has also a capacity because you cannot put too many wafers on the machine at the same time. So there is also a maximal capacity of the machine, which is here in this. I said it's very simplified from the reality, but a maximum number of wafers. Okay. Another interesting thing in this problem is that you have some setup time. Actually, for the machine to switch from one family to another family, it takes some time because, for instance, you may have to change the temperature of the machine. This looks like this machine. It needs some cooling time, and then before to start again. Okay. So, sequence-dependent setup times. We are getting to the end of the description of the problem. But there are another interesting thing. You have some chemical and physical properties that imposes some maximal delays between some pairs of activities of the same lot. For instance, here, between this step and this step, okay, you measure the temporal distance here, and then ideally you should not exceed a maximal time because if you wait too long, then this is very bad. So you have some kind of violation function. And this is not me who invented this function, but the customer said that this makes sense to have this kind of function. This is you have no violation if x is lower than a, then you have a flat violation if it is greater than a threshold, and then you have some kind of quadratic behavior here. Okay. So what's the objective function in this problem? Actually, it's a big criterion objective. The first objective, because this is very important, you want to minimize the total violation of these maximal time lags between steps. And the second one is to minimize the weighted tardiness cost of the lot. So you have the due date for the lot, so you have an end time for the lot, and if you finish after the due date, you have a priority. This is weighted by the priority, so you will want to minimize the weighted tardiness. To have an idea of the problem size, this is a bit the largest problem size, but in a single problem, you may have to handle up to 1,000 lots, okay? And let's say for each lot you have maybe 5 steps. So at most you have 5,000 lot steps, 5,000 steps in your schedule. You have about more than 100 machines, and well, you can have up to 10 candidate machines for a step. Okay? So the problem is not completely small, and the customer would like to have as a time unit 1 minute. Okay, the schedule horizon is 2 days. So if you think of the time unit in the CS schedule, you have about 3,000 time units on your schedule. Okay, I finish with a description of my introductory example. And then if you want to have 1 or 2 minutes to think how you would solve this problem using your favorite tools or whatever, you can think a bit about it. If someone has an idea, you can say, of course, the problem is difficult, so I'm not asking that to have a solution right now, but I don't know.
Do you have resource sharing in this problem? Resource that you share between?
Yes, because all the, all the machines are shared among the steps. Yes. Yeah. And it can be even that for the same load in the chain of step, you use one machine and then the same machine again. Maybe if it's load, it can perform this task.
I don't know. So will it make sense to hybridize programming and linear programming? Kind of hybrid approach. So
probably yes. You think of maybe something like
to do it by hand.
To do the batch, for instance, to batch together the different steps on the machine, and then using some CP Optimizer. It's probably a good way to approach the problem. And actually, that's how it was done in the original system where I said we are working with the customer on this, and that was the kind of approach that was used at this point. Basically, using some MIP to build the batches, okay, and then after using some heuristic to schedule. Not CP in this case, but heuristics. Okay. Now this is I will show you a problem that after this tutorial, at least you will be able to solve it with a 50 lines model that I will show on the slide, and we achieve quite, and even we can say very good performance. Okay, so I will show this model during the tutorial.
What do you mean by up to 10 candidate machines per one step? I thought each machine is
because not one step is not allowed to be processed on all the, I said there is 100 machines. It's not all the 100 machines that can perform this task, because the machine have some specificities, okay? So some cannot process some steps. So this is the number of candidates. For a given step, there is 10 possible machines where you could execute it. And you have to choose which one, of course, in the schedule. So the decisions, the main decisions of the problem are which machine you choose for the steps, okay? How you sequence the steps on the machine, how you perform the batches together, and so on. Okay, so I'm finished with the preamble. And this is the overview of the tutorial. I will do a short introduction, and then the big part will be this modeling part. And I think that it will completely occupy us for the first part of the tutorial. And then in the second part, there are many topics, but it will be much faster, and as you will know everything from the first part, it will be very easy. Okay, so first I should say, why this tutorial? Because I think CP Optimizer is not enough known in the scheduling community. It's not enough known by people that are using mathematical programming, because each time I go in conference, that in operation research, each time there is a scheduling problem, everybody, because it's their background, they first start a MIP model for doing that. And, well, that's fine. We will see. But quite often it is much easier to try a CP Optimizer model, and then at least you can see very easily if it works or not for your problem. It is not known by people using meta-heuristics, I think. CP Optimizer uses meta-heuristics inside. Okay, I will say a bit more about it later. It is not especially known about people that are using CP in general, because people tend to think that CP Optimizer is CP. We will see that it's far from being only CP, and there are many differences from a modeling point of view, many. And but this is maybe more logical. It's less known by people that are doing AI planning. As I say, CP Optimizer does not really address AI planning, but at least it enlarges the scope of classical scheduling problem in direction of planning. And I should say that sometimes there are some misconceptions of what it is, because maybe people have some, even if they don't know CP, for instance, they have some ideas, they've heard some things, some people speaking about CP, it's good for that, it's not good for that. We'll see that, well, CP Optimizer is not exactly CP. Okay, so this is the conclusion, and we will see after in the end if I manage to convey these ideas. I want to try to convince you that CP Optimizer is easy to try, easy to learn, because we will see most of the modeling concepts in this tutorial. It's very easy to use. It's powerful for solving complex scheduling problems. If you're a student and teacher or researcher, it's free. So something, and most of all, it's very fun. Very fun. Okay, so this is actually, if you're using MIP, and maybe you're using CPLEX, maybe you're using other tools for MIP, but if you're using CPLEX, you already have CP Optimizer, so it's delivered together. It's the same in the same product, so you can try it if you didn't try it. Okay, I said that it is not known enough in the scheduling community. Well, if you look at there are some trend a little bit, and if I try to search CP Optimizer on Google Scholar, and there is really some kind of growing number of citations.
Just a question. You said it's included in CPLEX.
Yeah.
So what are the main differences?
You will see the differences. You will see the differences during the tutorial. Don't worry. Yeah. But you will also see the common point, because there are many common points. Okay, so as I said, many people are using MIP for solving scheduling problems. Well, there is good reason for that also, because there are many advantages. First, and a very big advantage, is that it's a model and run. So you focus on providing a good model. You do not worry too much about how it is solved. And okay, you just press the solve button and then you get some results. Second advantage, it's an exact algorithm. So you have optimality proofs, or if the system cannot find a proof, you have some gaps, and it gives you some guarantee on the optimality of your solution. This is very important. But there are also many pain points when you're dealing with scheduling problems. First, modeling scheduling problem is quite difficult in MIP. The second point is that when you're in an industrial context, you need always to change your problem, because the requirement changes, the problem changes. And when you need to maintain and to extend these models, it's very, very difficult. The second problem is the limitation of the model itself. Because in fact, all classical formulation of scheduling problems in MIP, they tend to have very large number of variables and constraints. Well, there are not that many classical formulations of scheduling problem. You have time index formulation, for the one who know MIP. You have time index formulation, you have disjunctive formulation when you have unary resources, or event-based formulation. In all these problems, as you have a size of the problem that depends on the number of time buckets you choose to discretize. You need to discretize your problem if you have a time index formulation. Or if you have disjunctive or event-based formulation, you will have a quadratic number of constraints. Okay, so this leads to quite large models. Usually it depends on the problem, of course, but the LP relaxation is not very good. So it makes it quite challenging to handle real-sized problem, I would say. And if you read the literature, the papers, quite often when you have MIP models for scheduling problems, I've seen that quite often you attack problems with a few hundreds of activities, but in real-world scheduling problems, I say you have several thousands of activities to handle. Okay. The second type of techniques that are used is meta-heuristics. Meta-heuristics are very good. If you have some very smart people implementing a smart meta-heuristic on a particular problem or a particular type of problem, you can get excellent results, of course. But there are some pain points too, because there is not always a clear separation between what's the model and what is the resolution, I would say. You also may have problems where maintaining this code, and especially when the requirement changes. So it's also a bit difficult when you have complex constraints, because when you enter into some feasibility problems, even finding a feasible solution when it is not trivial, you may have difficulty with meta-heuristics. And of course, you have no quality guarantee, at least directly provided by the meta-heuristic itself. And the fact is that, yes, when you're working in an industrial context, you often need a fast assessment on what are the different approaches to solve the problem. And as I say, you have often tight deadlines for working on the problem. So if you're working on meta-heuristics, then quite often maybe you need to have a PhD working on your problem, for instance. And it can give very good results, but you need, at least the company who do that, need to have some time and need to have to take care of some risks when doing this. Okay, the third type of approach is what I would say is classical constraint programming. By classical constraint programming, I'm meaning integer variables and then some so-called scheduling constraints like disjunctive, cumulative constraints. For this type of problems, for this type of systems, modeling is easier than MIP, and especially for academic problems, because you have these disjunctive, cumulative constraints. Another advantage is just like in MIP, you have a clear separation between the model and the resolution. You usually have exact algorithms that provide some optimality proofs. But if you are looking at the details of industrial scheduling problems, you will find that some features are quite hard to model in classical CP. For instance, I list here some of them. When you have optional activities, when you have multimode, if you have a multimode RCPSP, you can easily find a model, a CP model. It's not very elegant, but you may be able to model it quite easily. But some difficulties also are where you have some calendars for the resources, where you're handling some batches, like in the introductory problem I provided, when you have setup times, etc. So there is one thing, some features of the problems can be difficult to model. The other thing is that there is no real efficient out-of-the-box and generic resolution algorithm for scheduling problem in classical CP. What I mean here is that as soon as you have objective functions that are not only make-span, okay, everything you see is not that efficient. Well, that's maybe a bit a subjective appreciation of this, but in any case, it's... And also, remember that we want to handle large problems, quite large problems. And often, when you try classical CPs, especially on large problems, you can end up with very long propagation times and so on. Actually, classical CP focuses a lot on constraint propagation. There are a lot of very smart constraint propagation algorithms, but when you're handling large problems, this can be heavy to have all these propagation algorithms, and this can be very long. Okay. So now I speak more about CP Optimizer. The CP Optimizer approach is, first, it's like MIP, so it's a model and run, okay? So just like in MIP, you focus on a mathematical description of your problem, okay? You do not need to worry, under a certain limit, about the real solution of the problem itself, okay? So what we did in CPO is that we have just introduced in the combinatorial optimization framework some additional concepts for scheduling. Because of this, so I will describe these concepts, of course. Because of this, modeling is much easier, modeling is faster, and the models are usually much more compact and maintainable than MIP models, for instance. So we will see that CP Optimizer has quite good out-of-the-box performance for real-world problems. And inside CP Optimizer, you have an exact algorithm, just like MIP, but it's an hybrid algorithm, okay? So if you think of CP as just exploring one search tree, forget it. CP Optimizer is not working at all this way. It's an hybrid method using some meta-heuristics, but it's combined with some complete algorithm. Okay? Now, if you want to use CP Optimizer is available under very different programming APIs, okay, and languages. So you can, the native language is C++, so you can of course write your model in C++. It's also very convenient quite often to use optimization programming language. So if you're using CPLEX, maybe you're a user of OPL, so you can use OPL for modeling in CP Optimizer. We have also a Python API, we also have Java and C# APIs. And then, once you have built your model, well, classically, there are two ways to solve it. Either you can solve it locally or on the cloud, because with IBM we have some services on the cloud to solve your model. Okay, so CP Optimizer is a particular combinatorial optimization framework. Okay, so these are the concepts that you find in all the combinatorial optimization framework, and that we will find in CP Optimizer too. If you are working in math programming, in constraint programming, you have this. You have what? You have constants. Okay, constants are parameters that will define an instance of the problem. For instance, A equals 0,0.2. This comes from the data. You have variables, decision variables. Variables are defined as an unknown. You need to have find a value, and it has a domain. Okay, so either, for instance, X is belong to the domain 0, 10, or you may have a Boolean variable, and the domain is 0, 1. Okay. You have expressions. Expressions are arithmetical combination of variables. You have this is if you are working with me for linear programming, you have linear expressions, of course. But the advantage of working in more general framework, like CP and CP Optimizer, you can have other expressions, like, I don't know, the logarithm, for instance, modulo expression. Well, almost everything you can think of. So we have expressions. You have constraints. Constraints allow to specify some illegal combinations of variables. So x less than y, in CP all different, x, y, z. Okay? And then you have an objective function that is to minimize or maximize a given numerical expression. Okay? So, for instance, in linear programming, you only have a subset of this. You will have only continuous variables and linear expressions and this bounding constraints. In classical CP, you will have, I would say, integer variables, a large set of expressions, and then this so-called given catalog of constraints. Okay, sometimes, well, there are some systems that have the catalog of constraints in CP is about 300 maybe, or global constraints. Okay, in CP Optimizer we have much less. What we do in CP Optimizer, we keep this general framework, of course, but we will add new instances of new types of variables, new types of expressions, and new types of constraints. This is all, if you want to summarize. And so the problem we find with math programming and with classical CP is that why it's difficult to model the problems is that it's not really using the right abstractions to model scheduling problems. Okay? Basically, what you have is only numerical variables, numerical decision variables. And this makes it hard to capture what is the essence of scheduling problem itself. And the essence of scheduling problem itself is it's time. Okay? It's a dimension that is, well, you cannot go backward, okay? It's always advancing, and it is fundamental, okay? So this is a different kind of visualization for scheduling problems, but I find it nice to illustrate the concept we have added in CP Optimizer. So it's quite natural to add some kind of concepts that are as mathematical as integer variables. We have the notion of interval. Okay, so we have a mathematical notion of an interval. Here in scheduling problem, it will be an interval of time. You have the mathematical notion of sequences or permutations over intervals, and you have the notion of functions of time. Okay, this will be some kind of first-class citizen in the model. Okay, so now I will go through, and until the end of this first part of the tutorial, I will go through all these modeling concepts a bit in detail, in order that you have a more precise idea of what are these concepts and how to use them in a model. If you want more details about these concepts, there are 2 papers that were published some years ago at FLAS conference, and they go a bit more in the detail of each concept and provide some formal descriptions, if you want, of this.
Are there still modeling elements that are available to describe topology of the system, the sets and disjunctive groupings and things, so assignment of machine to, so descriptive nature of the problem that are not translated into variables and elements in the...
All this descriptive feature will be translated directly in constraints or expression. We will see that. Sure. So, there is some little mnemonic here, because each of the concepts is either constant, a variable, and expression of constraints. Okay, because we are in a combinatorial optimization framework. So, what I will do is that I will put here one of these symbols depending on the concept I'm describing, either it is a constant, a variable, an expression of constraints. And there is really nothing new. I mean, all the things fall into this category. Okay, into these categories. So, one thing is that when you're dealing with combinatorial optimization, in general you have constants. In MIP you have constant. Constant is 2.3. 2.3 is constant. Okay. I said scheduling is reasoning about time. So, if you are constant, if you add the temporal dimensions to this constant, what you will get is a function of time, but a constant function, a known function of time that is not a decision variable of the problem. For instance, so that's why we introduced this notion of piecewise linear function in the system. I want to say that in the tutorial I will mostly use the OPL syntax for giving you an idea of how you write the things. Do not worry too much about the syntax if you do not understand the syntax. It's just giving you an example of how you write this in OPL. And what I want to say is that all these concepts are available in all the APIs, in all the languages. So, of course, you can define a piecewise linear function in Python, in C++, or whatever. But the syntax, of course, will obviously be slightly different. Okay, the first constant structure we'll see here is a piecewise linear function. What for? So, because I will try to explain for each of these concepts why is it interesting. Okay. Because otherwise we would not introduce this type of concept in the model. Piecewise linear functions, they are mostly used to model some temporal preferences or some earliness, tardiness cost in the schedule. So this is an example of how you define a piecewise linear function that is, okay, this value here, then it is 0 between 100 and 200, and then it's non-continuous here, and then there is a slope until the infinity. So you just say, okay, I say I won't describe the syntax, but it say, okay, you have a given slope here until time point 100, then it's 0 until 200, and then you have discontinuity and blah, blah, blah. Actually, if you're using CPLEX, it's the same notion, okay, of piecewise linear function as you find in CPLEX. What I should say is that we have the same type of model. We have some common objects in the model with CPLEX, and particularly, for instance, piecewise linear functions. Okay, so if in your problem at some point you want to express some earliness, tardiness cost, you should think of, okay, if it is piecewise linear, or maybe you need to approximate it with a piecewise linear function, you can use this type of object in the model. Constant. We have also the notion of step function. We will see how they are used, but quite often it is to model some calendars. Okay, so you want to say that the resource is available 100% of the time, for instance, I don't know, during some days in the week, then during the weekend it's not available, so it's not working on the activities, it's not processing the activities, so here it will be 0. this kind of intensity of work of the resource. And then maybe, I don't know, on Friday it works only half time, so it processes the jobs twice less fast. Okay. Again, don't worry too much about the syntax. You can define this. Piecewise linear, stepwise functions. And all these numbers come from the data, of course, in general. Okay. The last constant structure that is quite very useful and that we use is the notion of matrix, especially what we call transition distance matrices. And this is used when you need to model transition times, if you are solving some TSP, for instance, it may represent some travel times between different locations. Okay, and this is a matrix. So this is basically a matrix. Indexed, we have some index, and then you have some value in the matrix. In OPL, we have a kind of maybe strange syntax for defining this. Is a set of triple. It's say between, for instance, index for type 0 and type 1, the value is 30. We will see what it means index, what it means this value. This is depend on the context, how you use this in the model. But this is a matrix. Matrix whose value is known, whose value is you can read in the data. Okay, we have seen all the constants. Now, let's go to something more interesting. It is the notion of decision variable. And the main notion of decision variable that is introduced in CP Optimizer is this notion of interval variable. I said that when you're dealing with time, the notion of interval is something that comes naturally. Okay, this is an interval of time. So in general, it's used to model an interval of time during which some kind of property holds. Property can be, this will depend on your problem, that maybe an activity is executing, okay, between the start and the end of this interval, or that maybe a resource is free, or that maybe, I don't know, you have some kind of reservoir, some kind of tank, and then during this interval it must remain empty, for instance. Okay, so you can express some kind of, in the sense of planning, some kind of condition that must hold during this interval, for instance. What I want to say is that an interval variable does not necessarily represent an activity or something like that in the schedule. It's, in the general sense, an interval of time. Okay, and this is how we define it in OPL. This is, I give you an example. This is a dvar, is a decision variable of type interval. Okay, it's called x. This variable is x. Then you give the domain of the variable here. So you give a minimal start time, maximal end time. Okay, so it must be scheduled between 0 and let's say 1 million here. And this is the size of the variable. The size, for the moment, think of it as, if it is an activity, as the duration of the activity. Of course, it doesn't have to be fixed. It can be a decision of the problem itself. So here, for instance, we have, let's say, maybe x is an activity, and the duration can be between 100 and 200. Okay, and then it's part of the decision to decide how long the activity will be. Any question? Okay. A property of interval variables, well, is that, well, interval variables are variables, okay? So they are mostly defined by their domain, okay? So what is the domain of an interval variable? Or what can be the value of an interval variable? The value of an interval variable is an interval, of course, okay? So if you think of the domain of an interval variable, it's a set of intervals. Of course, we do not enumerate all the domains here. We have some kind of compact representation of the domain internally in the engine, okay? So we'll have the minimal start, maximal start, etc. We maintain only some bounds on the current domain of the variable. But if you want to think of it really as a variable with a domain, then we should have enumerated all the possible values for this variable, okay? Of course, here it's used. And as I said again, actually CP Optimizer never enumerates, because we make the assumption that time has a continuous nature, okay? So in the search, we never enumerate time. That's what I just, do not worry too much about the search, but I mean, what I want to say is that in the model you can easily, and that's the reason why I gave this example, you can easily have in the interval variable with domain ranging from 0 to 1 million, not a problem. It will not take more place, or even do not impact the search very much more than if the variable would be I don't know, between 0 and 1000. Okay. Okay. Now, maybe this is the most important slide of the tutorial, or next one, and this one, because there is a fundamental notion that is added to this notion of interval variable, and this is the notion of optionality. Okay? So, you can define an interval variable as being optional. What does it mean? It means that it is part of the decision of the problem to decide if this interval variable will be, we call this present or absent in the schedule. Okay? For people who are, and most of the people are used to AI planning here, so you can really think of this as the fact it's either present or absent in the plan you generate. Okay? And of course, the difference is that here we are a bit more restricted because we will have to start with an envelope of possible interval variables. Okay? But it will be part of the decision of the system to decide if the variable is the interval variable is said to be optional. It will be part of the decision to decide if it is present or not in the solution. Okay, and what for? So we will see many use cases of that, but it's used for when as soon as you want to model optional activities, for instance, if you want to have an activity that has alternative modes, okay, for executing the activities, then you will have basically one optional interval variable for each mode. Okay, that's quite easy. Actually, we will see, and it's a good if you are doing CP Optimizer model. Yeah.
Sorry, I'm a math programming column. Are interval variables bounded within the time domain like a normal variable, or is that actually it's attached to the interval variable? If I want this optional arbitrary length interval to occur or not occur in the problem, can I restrict where in the time domain it may appear or not appear?
Yes.
Start before.
Yeah. So the optionality is completely related with the interval variables it is defined on. Okay. But if, as you say, you want to say that okay, you have let's say an activity that can be executed either in this time window or in this time window or in another time window. Well, we will see we have several ways to model this, but one way to do this, and in some problem it's a very nice way to do it, is that you would have one interval variable that represents your activity, and let's say you have 3 time windows. You will have 3 optional interval variables, each of them with a domain that is restricted to be inside the time window, and you would have, we will see this, some kind of constraints, we call it alternative, that say, okay, we have these 3 candidates are the alternative for realizing the other interval variable. We will have next. So, yes, a good guideline for designing good CP Optimizer model, at least an ideal case, is when you can model all the discrete decisions in your problem. So, you have continuous decisions that are basically the start and end times of the activities. But if you can model all the decisions, discrete decisions, using, and we will see some example of this notion of optionality, Boolean optionality, and constraint between this Boolean optionality, this is already a good sign that your model will be solved efficiently by CP Optimizer. Okay, so I will define now more formally a little bit what it means for an interval to be optional. In fact, it's just an additional value in the domain of the variable. Okay, so more formally, if you define a variable x as being optional, it means that the domain of x, okay, is included in a particular value. Okay, I call it bottom. It means that the interval is absent. So if the search fixes the value of this interval to this, it will mean that the interval is absent. And we will see what it means for the constraints, for the expressions, but it means that it is absent. Okay? We will say it is absent. Otherwise, the value is then an interval of integers. Okay? And in this case, we say that the interval is present. Okay. And so, all the constraints and expressions that we will see and that we have been introducing in CP Optimizer, they will have to specify how they handle the case when the interval variable they hold on is absent. Quite often this is extremely intuitive. But at least when you formally describe the constraint, you have to take care of these values. So yes, this notion of optionality is something very fundamental in CP Optimizer model, and you really need to really understand. In the beginning, I know it's maybe a bit difficult to understand and to fully leverage this concept. But when you get used to model with CP Optimizer, and you will see that it's very, very, and very fun, by the way, to use also for modeling this. Okay. I will go very fast here because I think I'm running late. On an additional concept that defines actually the notion of size and length and intensity function on interval variable. The problem is, well, quite often you have some resources, for example, that suspend the activity, their activities. If you have a resource, some workers that it doesn't work during the weekend, okay, so you want to suspend the activities during the weekend. So there is a difference between what we call the size of the interval, that is the quantity of work required by the interval, and the length of the interval, that is its duration. So, and I will go fast here, just jump to an example. So you can, this is where we use some intensity function, which is a stepwise function. This is a constant we have seen before. So you can say, okay, this interval variable x has a size of 125 and use this intensity function f. It means that this intensity function, this is the same as we have seen in the constant structure. It means that this is the intensity of work, if you want, in percentage. So here, okay, during 50 time units, it will use 50 time units of the length. And then, well, what I want to say is that the size corresponds more or less to the area, okay, under the value. So if you think of intensity function as being only 100% 0, okay, it just means that if you have an interval variable of requiring a given quantity of work, it will be suspended during the intervals where the step function is 0. Okay. But by default, if you do not use this, we assume that the intensity function is always constant and equal to 100%. So in this case, there is no difference between the concept of size and length of an interval variable. And I think that in the examples I have, we will never use this again, but this is something that is very useful in practice. Okay, and you have also, so this is maybe the first type of constraint we see. It's forbid start, forbid end. This is just a constraint that say, okay, if, for instance, forbid start x f, it means if interval x is present, then it cannot start at a time t such that the function here is 0. Okay? You had a question about how we could represent some disjunction of domains. Another way is to use this forbid extent. Okay? So you would use only x as a decision variable, but you would have a stepwise function that is 1, 100, whatever. Non-null on the interval where on the segment, on the time windows where the interval can go, and 0 otherwise. Okay? So this means that the interval will have to go into one of the holes in this function. This is an alternative model for this. Okay. Let's switch. Okay. So, when you are dealing with scheduling, of course, one important constraints are precedence constraints. Okay. Of course, in CP Optimizer, you can model this. We have a set of constraints for modeling this, but it boils down to simple temporal networks. Okay. If you know simple temporal networks, so you can express all type of constraint if t, ti, tg are the start of the or the end of an interval variables. You can model this type of constraint with some delay, but interval variables can be optional, so you have to handle what happens when the interval is optional and it is absent. Okay, so this is why I say that it is simple temporal network, but it is reified by the optionality statuses. So, for instance, we have a constraint n before start, x, y, x, g are two interval variables, and z is a delay. It can be a constant, it can be an expression, a decision variable, integer decision variable, or whatever. the semantics of this constraint say if xc is not absent, so if xc is present, if both intervals are present, then the start time of xi must be greater than the end time of xi plus the delay. Okay, so and we will represent this with using this kind of picture. Yeah, but remember, this is always reified with this present status of interval variables. Okay. Okay, so we have kind of typology of different constraints, but this is just to cover the simple temporal networks. So simple temporal network. So you have end before start before start, etc. Okay, nothing too complex here. Okay, one thing that is important to know also is that the precedence constraints, they play a special role in the engine, and they are particularly optimized. We especially take care of them. Okay, so in particular, they are aggregated into a special structure that we call the precedence network. I will say more in some sections that describe a bit what happens under the hood, but we have dedication constraint propagation algorithm for this type of constraint, for this temporal network, and also they are exploited as an important structure of the problem during the automatic search. Okay, the second type of constraint that we will see here is what we call logical constraints. So first, there is an important unary constraint on the interval variables. Is the constraint that says that the interval variable is present. Okay, this constraint means if x is optional, it means that it is present. So its value is not the absence value. Okay. So why is it useful? Usually not to say that an interval is present or not present. If you know from start that an interval is not present, then you don't need to say that the interval is present. Maybe you do not need to model it at all. But where it is very useful, it's when you combine it, and especially when you combine it with binary constraints. For instance, you can say if x is present, then y is present, and if x is absent, then y is absent. They have the same status. Okay. We represent this with some kind of picture like this, with some implications actually. Okay, why this is useful? Suppose that you have, we will again see some examples of that, but suppose you have some task that can be decomposed into, you need to do A and then B. But this task, this global task is optional. Okay, but if you perform this macro task, let's say, you need to perform A and B. So you need to say somewhere in the engine a constraint that if A is present, then B is present too. Okay, they work together, so in the same connected, strongly connected component of the implication graph, I would say. So also in CP Optimizer we pay very special attention in the engine about this binary constraint between logical statuses, and also when you can say that if X is present, then Y is present. Okay, this is very useful in the models. So if you look at this binary constraint, of course you have some kind of expressivity just like 2SAT, okay, on these Boolean statuses of presence. Of course, in CP Optimizer you can have much more complex constructs, okay, between this. You can say, okay, this is not a realistic example, but it's just as an example, you can say that if X and Y are present together, then either U or V must be present. You can say that. But this type of constraints, if you can avoid them, it's good. What I want to focus on mostly is this type of binary constraints are very important, and usually you capture most of the problems related with present status with this.
Excuse me. Are the first two completely equivalent? The first two constraints, examples. Are they completely equivalent?
To set?
Like you said, if X is present, then...
Yes, in this case it's an equivalence.
Completely equivalent?
Yes, in this case, yes. Yeah. It's an equality. So if one is present, those is present. If one is absent, those is absent.
Okay, the first two, also the implication. It's completely equivalent to the implication.
The implication means
if the first two examples.
They're different. I mean, there's not the.
But the meaning is if
the meaning is not the same.
if X is present, then Y is present.
Yeah.
And also the second, right? Or am I wrong?
You could have Y can be present and X not present here.
Yes.
Sure.
Okay, right.
And it's
Sorry.
really an implication.
Understood.
So, okay. Again, this is the same story. Logical binary constraints, they play an important role. They are also aggregated in what we call a logical network, which is kind of two-sat networks, two-sat implication graph, okay? And then we'll have dedicated constraint propagation algorithm, and then, again, they are exploited by the search. Okay, then I will do a little parenthesis on complexity. This is mostly for fun, because it has no impact in practice, but it's curious. I find it curious. If you look only at precedence constraints, so this is a simple temporal network, this is polynomial. This is a polynomial framework. You can easily find in a simple temporal network a solution. It's polynomial. If you only look at the logical constraint, binary constraint, to that, it's also polynomial. The interesting thing is that when you mix them together, so you see, we had at some point the temporal dimension and then a little dimension here on the logical status, then it becomes NP-hard. And the proof is very simple because, in fact, you can express a temporal disjunction between two intervals, so x, y, that says they cannot overlap, so x is before y or y is before x. You can express it only using this type of constraints. Okay. I maybe won't have time to explain, but it's explained here by this figure. If you want, you have basically you have two optional intervals for x. One that will represent the possibility that the case that x is before y, and the other that represent the possibility that y is before x. Okay, and then using this constraint, well, you say that you have an equivalence here because you are either in this situation or in this situation. In the first situation, you have a precedence constraint that say x1 is before y1, and in the other situation, you have the other precedence constraint. Okay? That y2 is before x2. If you look at the OPL model for modeling this, okay, well, the first thing I want to say is that, okay, this is the first CP Optimizer model we see, kind of complete. Never use this in your problem if you want to express the disjunction between two intervals. This is just for, really for curiosity, I would say. Of course, we have much more efficient way to say that x and y should not overlap. But this is how it looks. So you would define x, y, the two interval variables. This x1, y1, x2, y2 are optional, and then you add this constraint. You have a set of constraints, and then start at start, etc. Okay. I won't describe this problem, this model, but you can have a look with fresh. It's very easy. Okay. There is another pattern that we can see that is much more useful in practice. It is this one. You are given, this is in OPL, this is an array of variables. So you're given a set of n interval variable xi, so x1, x2, x3, xn. And then the constraint you add is some precedence constraint here. You have a chain, okay? x1 is before x2, x2 is before x3. But all these intervals are optional. And you have some implications. So x2 implies x1. x3 implies x2, etc. So what does it mean? It means that, so we call this pattern because it is quite recurring in the models often, a chain of optional interval variables. And it is useful if you want to model a situation where you have a set of n intervals, okay, that follow each other. But no, actually you do not know how many intervals you will have in the end. But you have a chain of k intervals and you do not know k.
Is there a shorthand for that, or if you have
No.
structure?
No, there isn't. When I say it's common, it's not in every model you find it, but I would say this is kind of pattern that you kind of need to know. No, there is no pre-defined way to say this. Okay. So we have also expressions of interval variables. For instance, you have integer expressions. Oops. Of course, quite often you have an objective function, so you need an expression that represents the cost. Okay, for instance. So you have expression to get the start, the end, the size or the length of an interval variable. And this is so. So what it returns is an integer, okay, an integer expression. And again, we have to take care of the fact the interval variable may be absent, okay. So for that we provide what we call an absence value, okay. So this expression start of x v is a constant integer, means that the value of the expression is v when the interval is absent. Otherwise, it is the start of the interval variable, and this is perfectly defined. If x is absent, then you will have this value, and if x is present, then the start is perfectly defined, so you can return the start x. And this is an integer expression. By default in the model, this is 0. Okay, so when you write just start of x, you have to know that if x is absent, it's 0. Sometimes it's maybe can lead to some problems, but if you are not happy with this value, you can change it. So what I want to say, this is a typical example of a make-span objective. Okay, you want to minimize the maximum for all this xi of the n time of this interval. Okay, here it's good, even if the interval are absent, the default value is 0, so hopefully, as you want to max, you can get this way the make-span, even if your set of interval variables, in your set of interval variables, you have optional ones. Okay, we have also some slightly more complex expressions that take a piecewise linear function as input and will evaluate the function. For instance, start eval x f v says that okay, the value will be v if the interval is absent. Otherwise, it will be the value of the piecewise linear function f at the start of x. Okay, an example here. Again, I take the same piecewise linear function as I described in the constant. This is defined, and then you want to minimize here. You want to minimize. This is kind of earliness, tardiness cost. Okay, so you want to evaluate the n time of this interval variables on this function. And interestingly, if the interval is absent, this expression will return a value here, vi, that you decided what to do. It can be used to model a non-execution cost for an activity, for instance. So once in a row, you have here an earliness, tardiness cost and a non-execution cost for your activity.
Is the piecewise linear function locked to the task, or can you have functions which are absolute?
It's not. It's absolute. Yes, it's absolute. Yes, the value are absolute. Yeah, absolute. Okay. Just to say this one, that we have also an expression to measure how much an interval variable overlaps a given time window or another interval variable. So you have two interval variables, x, y. Okay, this expression tells you what's the length of the overlap between x and y, if both intervals are present. Otherwise, again, you can specify the value you like. Quite often it's 0, because then the default is 0 here. This is useful if you have some kind of energical constraints. You want to measure how much effort you spend in a given interval, for instance, and then you want to sum the contribution, the overlap of all this interval on another interval. Okay. Of course, you can aggregate this with all the kind of classical aggregation arithmetical expression in CP. Okay, so I mentioned this, of course, linear combinations, but it's not restricted to linear. You can have log, power, whatever, square root. Another important thing is what we call in CP array expressions. So, for instance, A is an array of integer or floating point, or even can be an array of decision variables, and it's indexed by x, which is also an integer expression, and it will return the value of of the variable or the constant of A at the index x. Okay. So now to answer maybe your questions about some kind of structural constraints in a schedule, because we have many structural constraints in a schedule. For that we have two main constraints for modeling that. And it corresponds more or less to some kind of, if you think of a hierarchical description of your problem, sometimes problems have a natural hierarchical description, And you can describe this as some form of AND or graph. Okay. You can also, it has many connections with hierarchical task network in planning, I think. But let's see some use cases. For example, in manufacturing, sometimes you have a production order, okay, and it can be executed following several alternative recipes, okay. For this order, you can do either this way or this way, and in a recipe, you have a set of operations with temporal constraint in between. Okay, but okay, then you have all the features of the problem. But another use case in project scheduling. Project scheduling, you may have a hierarchical description of the project. So you have a project, it can be decomposed into several tasks with temporal constraint between the tasks. And then for the task, either it can be a leaf task or you can decompose the task into a sub-project and so on. But also, there may be alternative ways to decompose the task. Okay, you can do it either this or any task in the hierarchy, either this way or this way or this way. So you see that in this case, you can naturally describe the problem, the hierarchical problem, as a form of AND or graph. And this is what we say here. So you have an order, then you need to select one of recipe, and then for a recipe, if you select this one, then you will have these operations. If you select this one, then you will have these operations. Okay. So for that, we have two types of constraints. What corresponds to the end is the notion of span. Okay. So span is a constraint between one interval variable and an array of interval variables. It says that if x, let's call it a kind of master of the span, is present, then it will span all the present intervals here in this set. So suppose that you have x, you have all these intervals in the set y, but only x1, x2, x4 is present. Then this will constrain x to start at the first activity here, at the first spanned activity, and to end at the end time of the last activity. Okay. And if x is absent, then all the y intervals are absent too. And what corresponds to an OR node is the notion of alternative. Here you have an interval variable x, and you have a set of alternative ways to, quite often it is used to model the fact you have a number of alternative ways to execute this interval variable x. This constraint, the semantic of this constraint means that if x is present, then exactly one of the y is present, all the others are absent, and the one that is selected to be present will start and end at the same time together with x. Okay. And this is very useful, and we will see this when we want to model multi-mode problems, for instance. Okay, there is a generalized version of this alternative constraint where you're given here k, which can be either constant or an integer expression too, and it means you do not want to select only one interval here, but k1. Okay, suppose that you have an activity and you need to select two operators for handling this activity. One way could be to say, okay, you have an alternative with cardinality 2, and you will select two of the intervals that represent the execution of the activity on a particular worker. Okay, I won't describe this in detail, but this is just again an OPL model that describes what I have just said now. This is kind of work breakdown structure here. This looks like a bit as a hierarchical temporal network. When you have a task, it can be decomposed into several ways, alternative ways, and we have decomposition. So this is what I said. And you have a set of, you see, you have a set of alternative constraints here and a set of span constraints. Okay, to describe your decomposition. Okay. So far, we have seen a lot about temporal constraints, logical constraints, some kind of structural constraints to model these hierarchical problems or allocation of different modes for executing an activity, for instance, but we have not said anything about resources. And resources are something very important in scheduling, of course. So there are three sections now. One is about interval variable sequencing. It means that it's kind of unary resources, okay, you can understand it as this. Then there is the notion of cumul function for cumulative resources, and the notion of state functions for function whose state changes over time. Interval variable sequencing. So what for? The idea here is to model for modeling constraints that, among other things, enforce some temporal ordering on a set of interval variables. But you do not know in advance the order of the interval variables in the sequence. Okay? Typically, this is a machine that can only perform one task at a time, like in the job shop. It can be in a TSP, a vehicle that can only perform one visit at a time. Okay? So, how does it work? This time we will create a new type of decision variable in the schedule. This is what we call a sequence variable. A sequence variable is defined, this is where it becomes a little bit subtle. It's defined on a set of interval variables, x1, xn. Okay? What does it say? You say, okay, this is in the syntax say, okay, suppose you have an array of n interval variables here, and you define the sequence p in x. Okay, you have, let's say, 6 interval variables. So it's a new variable. So we need to define is what is the domain of this variable, and the domain of this variable is a permutation, is a set of permutations of these elements in the sequence. Right? And it is a permutation of the present intervals. So in a solution, an interval can be either present, either absent. Okay? Here, suppose you have this variable. This is a possible value for this decision variable. Suppose that here in this solution, x2 and x4 are absent, and so they're not in the permutation. And this is just an ordering of the present interval of this. Okay? So this is a value at a solution for this decision variable. Okay? Well, so far, what I want to say here is that so far, this order here does not really represent a temporal ordering of the variables. I will say a little bit more later on this. So, it's a variable, it's a decision variable. So, naturally, what you want to do is to define some set of constraints that you can post on these variables. So, there are 3 types of constraints that you can post on it. First, sequencing constraints. Sequencing constraints are quite simple. It says, so for example, we have this constraint first, px. It means that if x is an interval variable, p is a sequence variable. It means that if interval x is present, then it will be the first one in the permutation, in the solution. Okay? Of course, we have the same thing for last. Prev means you have 2 intervals, x and y. It means that in the sequence p, if both intervals are present, then x appears right before y in the permutation. And something that is before, it means that x appears somewhere before y in the permutation. Let's take it on an example. This is, okay, you have a sequence variable with 3 intervals, on 3 intervals here, x1, x2, x3, okay? They are all optional. And you have only a constraint that says x2 is present. So the domain of this sequence variable would be this one. We do not enumerate, we do not represent explicitly the domain in the engine. But if we would represent it explicitly, the domain would be this one. Okay? So why? This is all the permutations where x2 is present, but x1 and x3 can be here or not. Okay? So you have x2, then you have all the permutation where you introduce x1, so x1 before x2, x2 before x1. You have a permutation where you introduce x3, and you have all the permutation where you have all the 3 intervals present. Okay? So this is the domain of your sequence variable. Now let's see if we had a constraint first, p1. This constraint says if x1 is present, it must be the first. Then this will rule out from the domain all the values where x1 is present and it is not the first. So this won't be possible, this won't be possible, etc. And etc. So if you had a constraint before in the sequence, x2, x3, it means that this will rule out this possible value because both are present, but x3 is before x2. x2 is not before x3. Okay, that's, and then you can keep it. So you can add this type of constraints on sequence variables. Now, I said, of course, if you use a sequence variable, quite often you want to say something about there is some relation between the order in the permutation and the temporal order of the interval variables. And this is the purpose of the no overlap constraint. The no overlap constraint says that, okay, it holds on a sequence variable, and it means that the permutation represents a temporal order of the interval variable. So if x5 appears before x1 in the permutation, it means that the start value of x1 is start after the end time of x5. Okay? Okay. So, and finally we can see maybe the first interesting, also I don't know if it is so interesting from an industrial perspective, but the first scheduling problem in CP Optimizer that we can see today is the job shop scheduling problem. Job shop scheduling problem. What you want to? This is a full OPL model for the job shop scheduling problem. Okay, you have everything here. You have a set of operation. Okay, so everybody knows the job shop scheduling problem. Okay, you have a set of operation with precedence constraints. Each operation should be executed on one of the machine of one of a given machine. One machine can perform only one activity at a time, and we want to minimize the maximum. Okay. So what you do, you define one interval variable for each operation. Okay, here it's a two-dimensional, but that's a detail. It's a two-dimensional array of interval variables. First by job and then by the position. For each interval variable, the size is the processing time. This is okay. We will suppose this comes from the data. Huh? This is the data. This is some processing time. For each machine, you will define a sequence variable on all the interval variables. This is here some filtering, saying that you only consider the interval variables at the position p that use the machine, a given machine. Okay. So let's suppose that here M is a green machine, then the no overlap will be defined on this operation. Operation 2, 1, 1, 2, 3, 3, and 4, 2. Okay. So here we have defined all the decision variables of the problem. The interval variables and the sequence variables. We only need to, say what's the objective function. This is a make span, okay, we have already seen this. You want to minimize the max of each job of the n times of the operations. And then we have two types of constraints, no overlap, because constraints interval on a machine do not overlap. So no overlap, all the intervals on the machine. You have a set of no overlap constraints, one for each machine. And you have a set of precedence constraints, okay, all these precedence constraints on the job. Okay. I think I will finish this first part of the presentation on this job shop scheduling. But now I make another parenthesis on the performance because it's really, I understand it's quite boring to go through all these modeling elements one by one. So this is a little parenthesis on the performance of CP Optimizer on job shop scheduling. On this model, exactly this model, not one line more. Okay. So job shop scheduling is probably one of the most heavily studied scheduling problem and maybe combinatorial optimization problem in the literature. Some people in a paper said that I didn't check, but that there is more than 60,000 references on Google Scholar about job shop scheduling problem. There are many methods that have been used, so MIP, CP, many meta heuristics, and still we were able in 2015 to improve quite a lot and close quite a lot of job shop scheduling problem. Famous instances that have been here since 30-40 years. But for this give you these instances, we have for many of these instances the upper bound where, because there have been so many mass of meta heuristics working on the problem, that the upper bound are quite often the optimal one, except maybe a couple of cases here where we were able to improve the upper bound. But because CP Optimizer is complete, we were also able to improve lower bound and close a number of problems. There has been a recent paper by Chris Beck and one of his colleague doing a comparison, quite in-depth comparison between MIP models, many MIP models for job shop scheduling and this CP Optimizer model. Actually, the main topic of the article was about comparing MIP model, but they also compare the best MIP models with CP Optimizer. And you can see that here, CP Optimizer is much faster than any of the MIP models for solving two optimalities, these job shop scheduling problems. Okay, And because MIP models, even the best MIP models, they stop to finding some optimality proof, I don't know, 12, 15 type of job shop problems. CP Optimizer was able to close some problem with larger size. This is very nice, but I want to say that, so this is very nice for CPO. CPO is able to prove optimality much better than MIP models on job shop scheduling problems. This is one thing, good. But you see the size. This is ridiculous. I mean, you don't find any industrial scheduling problem that maybe even just look like a job shop of this size, okay? The size is at least 10, 100, 1,000 larger than this, okay? And this is where, of course, for this problem, CP Optimizer does not prove optimality. And it's not tomorrow that we'll be able to prove optimality, but it provides also very, very good solutions, good quality solutions. Okay, I think that maybe it's time to make a break. I didn't advance at all as much as I expected, but this is not a problem. We'll continue going through the modeling element at some point, and then we'll switch to more detailed things. This will be a bit maybe as you wish. There will be things about more focuses on what are the performances of the CP Optimizer, how it's working under the hood, giving some element about that. Okay, we'll see something like that.
So I mean, I think I understand what it's good at. I mean, task scheduling, you minimize next span. You can have also maybe complex functions associated with the task. What is it not good for? Like really, wouldn't you be using
yeah, so the most challenging problems are when you cannot capture all the non-temporal decision variables in the Boolean, in this notion of Boolean status of interval variables.
Yeah.
And especially, so I'm not saying CPO is very bad at that, but this is really much more challenging for CPO. It's when, for instance, so we have not seen, we will see this after the break, but this notion of, for example, cumul, when you have an activity that can consume a variable quantity of resource, okay? And it's a decision to decide how much you consume. And if this is quite continuous variable, okay, if it is discrete, you can consume 2 or 3 or 5, that's fine. You model it with optional interval, perfect. But if it's continuous variable.
Is that because then, if you don't discretize time, you can get a non-linearity what you consume at the time?
Especially it's because, well, you need to have a way in the search to fix the value of these variables. And currently, CPO, we do things, but probably we should be more clever in the future to do that. Okay, so what we have seen so far is, as far as resources are concerned, how we can model these no-overlap constraints on a set of interval variables, on a set of optional interval variables. There is one important thing that can be added to the no-overlap constraint is the notion of transition distance. I explained in the beginning we have this transition distance matrix. So we can specify when we actually when you define a sequence variable, you can specify it in a way that you associate an integer that we call the type to each interval variable in the sequence. Okay, and this integer will be used to index the transition matrix. So in OPL, the syntax is when you define the variable, okay, you define the variable on all the interval xi here, and then you can associate something that is a types, and it says that in this sequence, interval xi has a type, an integer type, ta, that is known. Okay, this is something that is known in advance, the type. Okay, so. Yes, and as I said, type will be used to index transition matrices. What does it mean? It means that you can define an overlap constraint on a sequence variable together with a transition matrix M here. Okay? It means that, so actually there are two options of this no overlap constraint, because you have a Boolean here. I will say a little bit what it is, direct or indirect. But if you pass this constraint, so transition matrix M on the sequence variable P. It means that P will represent a chain of non-overlapping interval variables, of course, the present one, and you will have a transition distance M in between consecutive intervals, okay, indexed by the index of the interval variable. Actually, this is a little detail, but you have a Boolean parameter that tells if the transition distance is only applied between direct successors or also between an interval variables and all the successors. Okay, let's see an example. It's much easier to understand. So this is an overlap, okay? This is a transition matrix. Suppose that we have this, it's also a solution. So we have found this value for the sequence variable, x5 is an x1, then x3 is an x6. And suppose you have this type, x5 is of type 1, x1 is of type 0, and so on. So this means that you will have a transition here, transition time, that will depend on the index, on the type of the two intervals. So between index 1 and index 0, you have a transition distance of 15, okay? So you have a minimal delay of 15 between these two interval variables in the solution. And the distinction between this, if it's applied only on the direct successor or on all the successors, is suppose now we have this matrix and you are not applying it on not only on the direct successor but on all the successors. It means that, for instance, here you have x5 and then a successor that is x3 and of type 1 and 2, and here if you look at the transition distance between 1 and 2, it's 60, so it's maybe larger than this transition time. Okay, so in this case x3 would be pushed also. Actually the distinction makes sense only if the transition matrix does not satisfy the triangle inequality. Okay, so this is a little distinction. So there are two variants of the no overlap in this case. Okay, so yes, probably you have guessed the type of model we want to use this for. Typically, for instance, this is a complete model for a very vehicle routing problem with VRP with time windows. Okay, this is a complete model, even including the data here. So again, I won't enter in all the details, but what you do is that you have an interval variable for a visit. Okay, it's VRP with time window, so you have a time window for the visit. This is in the domain of the interval. Okay, each visit is constrained to be within a time window, and then we have an alternative, an optional interval variable for each visit on a given vehicle. Okay, this vehicle visit, it's called V visit, is an optional interval. It represents the fact, when it is present, that this visit is executed by, is that visit visit I is executed by vehicle G. Okay, and in this case we have little additional fact that, for instance, here we model the fact that the duration of the visit depends even on the vehicle. This is very easy to model here. And so what we do here, we have a sequence variable route for each vehicle, okay, that contain all the visits of the vehicle. Those are optional intervals. And what you want to do here, for instance, you want to minimize the end time of the, well, okay, no, this is, you minimize the sum of the return time of the vehicle to the depot. And then the constraint, you have no overlap, okay? The visits on a given route do not overlap, and you have transition distance, transition time, that are given by the matrix here. On the matrix may depend on the vehicle. It's not a problem, it's very easy here. What you say is that you have two visits that are special. It is a departure from the depot and the return to the depot. In this case, this visit, you need to have one for each vehicle. That's why they are present necessary. And you say that the departure from the depot, when you look at the sequence of a given vehicle route, the visit to the depot, the departure, is the first interval, and the return to the depot is the last one, okay, in the sequence. So we see illustration of how we use an overlap constraints and these first and last constraints on the sequences. And finally, you say, of course, that when you perform a visit, well, here all the visits are obligatory. You could even have a variant of the problem where you're not obliged to do all the visits, and you could maybe have an objective to maximize the number of visits you make. So it would be on a one line change in the model. But here, this interval present, the visit of necessary present, but you just say that, okay, you need to select one vehicle for the visit. Okay, so one of the optional interval representing the fact vehicle G perform visit I will be present, only one, and then it will be synchronized with this visit itself. So is it more or less clear, the general idea behind this model for the VRP? Okay. So we have additional expression on sequence variables. Expression, you remember, it's something that take a variable and return some integer expression. Because sometimes you need to have some more detailed post some more detailed constraint on the sequences. And for instance, you would like to know, okay, you are given interval x in the sequence, and you would like to know what is the type of the next interval. It's not known in advance because the sequence is not known in advance. But for a given interval, you would like to know the type of the next one. Okay? So this is the use case, the typical use case for this type of next expression. And again, here you have two special cases, because if the interval is the last of the sequence, then you have no next interval to which you can take the type. So you can specify a given value here. And again, also when x is absent, you need to specify a value for the expression. Okay? So you can specify this with this type of expression. And we have similar expression. You have type of next, but you have also the start of next. It means it will return an integer expression that say what is the start time of the expression of the interval variable that is next to a given interval in the sequence. Okay, and we have the same thing with the next and the previous, etc. A typical use case for this type of thing is when you have transition costs. Okay, suppose that you want to minimize. It's not transition time, okay, because this is something that will not push the next activity, but it's a cost. And here you can use again this type of thing. For instance, you would have a matrix of cost, okay, that is transitioning from a given type to another type is given in this matrix. And then what you would do here, if you maximize for the sum for each interval variable I of the element in the matrix that correspond to row Ti and the line and the column that correspond to the type of the next. Okay, so for a given element, you don't know which one is next. Okay, but in the matrix you will get the cost of the next one, and you will have no overlap. Okay. Okay, this is a typical use case for this type of expressions. Sometimes you have very complex constraints on the sequencing and say, okay, you want to have conditions on what is depending on when the next of a given interval starts and the delay, you may want to do something or other things. Then you can use this type of expression to say, okay, this is I know and I can constrain what is the start time of the next interval. Okay. Another very interesting thing is, because sequence variable are variable as other variables, you can also have constraints between sequence variables, between two sequence variables, for instance. And we have introduced a quite interesting constraint, actually two, which are very useful if you want to model things like first in, first out on some machines, or in general some spatial constraints like no bypass constraints. Okay, if you're doing some train scheduling, for instance, you know that if two trains enter a given segment, then they will not bypass each other, and then they will exit in the same order. So this is a constraint between two sequences, basically. I have a small example, and this we will see also can be very useful in stochastic scheduling. Is that with this type of sequence, with this type of constraint, you can do some stochastic scheduling where the objective is to build some robust sequences. Let's see. The same sequences, what does it say? You have two sequence variables, okay? And you suppose you have a mapping between the interval on the first sequence and the interval on the second sequence. Okay, here this is a color. Okay, just the same sequence means, well, if you have given a value for the sequence on the first one, then it will be ordered in the same way on the second sequence. Okay, here this is a color. Okay, just the same sequence means, well, if you have given a value for the sequence on the first one, then it will be ordered in the same way on the second sequence. Okay, here this is a color. Okay, just the same sequence means, well, if you have given a value for the sequence on the first one, then on the second sequence. There is no temporal constraint between these elements, but the order is the same. Okay, the order of the colors, for example, here is the same on the two sequences. And the same common subsequence is a little generalization of this, and it says that okay, at least the element in common between the two sequences, they are in the same order. Use case: suppose that you are, for example, in a manufacturing chain. I don't know. You have some. How is it called? Some conveyors, okay, between the machines, and you have maybe complex network of conveyors. You have a conveyor from machine M1 to machine M2, from machine M1 prime to machine M2, etc. And you have this topology, for instance, and you know that the items on the conveyor, they cannot bypass each other. Okay, so you would have some sequence. The machine is performing some sequence of work, and what you would do here is that you have a sequence variable for each machine and an overlap constraint on each machine, for instance. But you would say here that, for instance, you have the same common subsequence between P1, this sequence variable, and this one, okay, because all the elements in this sequence they will have to follow the same order in this sequence. So you see the pink one is before the green one, for sure. The pink one is before the green one. But they can, here, because the conveyor mix the items, they can mix a bit the same as they want. And here, for instance, this is the same sequence constraint, because the items are in the same order here at the beginning of the conveyor belt and at the end. Okay? So you can here easily model this type of constraints. I spoke about the stochastic scheduling example. Suppose that you have a scheduling problem with unary machines, but you have some uncertainties on the durations of the activities on the machines. Okay, you have some distribution or whatever, but here I put myself in a situation where you are able to distinguish between a set of scenarios that you want to handle. Okay, you have n scenarios, and for each scenario you have a particular deterministic duration for the processing of tasks by a machine on the sequence. So what you can do is some kind of two-stage. If you are familiar with stochastic programming, you have two-stage stochastic programming problem here, where the first stage variable will be the sequence. You want to build robust sequences, and then you will evaluate the cost on the second stage variable, which will correspond to the actual dates on the machines. So what you would do here in just one model, you would duplicate the sequence, one for each scenario, which particular duration, okay, given by the scenario, and then you would have a master sequence, and you would put the same sequence between all of them, okay, and then we'll just give this model to CP Optimizer and say, okay, for instance, I want to optimize, I don't know, the average cost across all the scenarios, okay, and CP Optimizer will build a robust sequence that kind of optimize across all the scenarios at the same time.
When you say robust, it means that it's valid for all possible scenarios?
Yeah, I mean, in a sense that it will have, let's say, it will be robust with respect to the objective function, and in the fact the duration of stochastic here. Okay, to summarize, I finished here with interval variable sequencing. To summarize, we have a notion of sequence variable, P. We have a set of constraints. First, last, this sequencing constraint, no overlap constraint, same sequence constraint. And then we have a set of expressions. Okay? Okay. If you are used to integrate classical CP systems, maybe you can ask, okay, well, we know this is more or less a disjunctive constraint in all these systems. Yes, that's true. But think of, well, the basic no overlap is a disjunctive constraint. But think of you would add all the features we have added around this sequence variable. For instance, transition distance, okay? Okay, you can add a new argument to the no overlap, to the disjunctive constraint, that is a transition matrix. This is fine. How do you handle transition cost? Then you would add again something additional in the constraint. that say, okay, you want to measure the sum of the transition distance by the constraint. This is what is called usually the circuit constraint, I think. But then, okay, but what if maybe you want to not aggregate the transition distance with the sum, but maybe with another aggregation? So you need another global constraints, I don't know. So that's why I think in many of these systems you end up with a catalog of 300 global constraints, because all these constraints need to do everything and everything and everything. Here our approach is more to extend the notion of variable itself when it's needed, so that you can mix, you have more lower bricks to build your models, and it's much easier to build. Or for example, if you're only a disjunctive constraint, how do you model a same sequence constraint between two disjunctive constraints? Disjunctive constraint is not a variable, so it's very difficult. Okay, and also the notion of sequence variable, it allows to extract some structure and to give some structure of the problem to the search, and the search exploit, of course, this notion of sequence variables. Okay. I will go here now, completely change the topic a bit, and address different kind of resources, which are more cumulative resources. So for that, we have introduced the notion of cumul function. I said quite at the beginning that scheduling is about time, and naturally you have this notion of function of time that enter into the play. So what is a cumul function expression? It's an expression, so it has a value. But as it's a function expression, the value of a cumul function expression is a function of time. Okay, and it's a function of time that can change over time, and whose change is incrementally changed by the interval variables. So the typical case is you have to model the number of workers that is currently working at any time point in the schedule, or the level of an inventory over time, for instance. So actually what we say is that we define the elementary cumul function, which corresponds to the contribution of an interval variable to a cumul function. And we will distinguish a few of these individual contributions. For instance, we have the notion of pulse here. Pulse x1 is a cumul function, an elementary cumul function. The value is 0 before the beginning of x. It's exactly equal to 1, for instance, here, or to a given value between the start and the end, and then it's back to 0 after the end time of the interval. Okay, we have a set of a few elementary cumul function. We have the notion of pulse here, step at start. This is something that increases the levels of the function at the beginning, step at end, and then we can also provide, instead of a given value here, a range of values. Okay, so it will be a decision of the problem also to decide what is the height of this function. And what you can do with this elementary cumul function is to combine them, okay, and then to build really what we call a cumul function. So what we can do here, we define a cumul function expression as the algebraic sum of elementary cumul function or the negation. Okay. That is the factor is plus 1 or minus 1, the multiplicative factor. Okay. Look, something interesting is that it's very similar. There is very similarity with the fact you have some kind of scalar expression and those kind of this functional expression. Suppose, and we will see it on an example, you want to model the multimode RCPSP. Okay, you have two types of resources, renewable resource and non-renewable resources. Non-renewable resources is something that is like money, for instance, that you use for executing the activities, but it's never returned. Okay, so you consume it, the activity consumes it. And if you want to measure how much you use globally in the schedule, you will have something like this. The interval are optional, but if they are present, you will have a price to pay that is Ci. Okay, this is a scalar. This is the value of this expression is an integer or a floating point variable. Now, when in scheduling you want to do this for every time point to measure the cumulative resource usage of something, then this is why you will use the cumul function expression. And this is very similar. You use the cumul function and it says this is a sum of some pulse, okay, and each interval variable, this is the elementary cumul function that we have seen, and so each interval variable xi contributes with a 8 ci to this function. This is an expression, cumul function, as a solution when all the interval gets fixed. Either they are absent, we will see if interval is absent, then this is 0, contribution is 0. If it is present, then you know the function, you know when the interval starts, when it ends. Okay? So when you sum up all these functions, you get a perfectly fixed stepwise function. Okay? So the value of a function expression as a solution is a function, a known function. An example, a very simple example. Here you have a function f, which is a pulse of x with 8, 4, minus pulse of y2 plus step at n 3. Suppose that the solution you have fixed the interval variables at these values. In the end, the values will be given by this function. Okay, you see? Because it is 0 in the beginning, then x contributed with a pulse 4, so it will add this, and then this is this function. Y, you do minus 2, so minus 2 here, clack. And then you have a step at n that 3, at end the level increases by 3. Okay? Is it clear?
So we're preventing inventories from going negative, falling. These pulses will presumably unintentionally add up to negative amounts representing negative inventory.
Yes, after we will just think right after that when you have an expression, just like you will add constraint on this. Okay, exactly, and this is my next point. Exactly, it's you want to post constraint on this function. Okay, so what kind of constraint you can post? You can say this function is, you have an integer, it's always lower than this integer. You write this, actually you write this, f is lower than h.
Is the constraint on the integral of the cumulative, or is it path? Does it apply all on the path?
This one, in this case, it applies on all the horizon, so everywhere, okay? But, yeah, good point. H can be a decision variable also. And this is very useful if you want to minimize the peak usage of a resource, okay? You will have this variable here and, for instance, minimize age or the sum of the age or whatever. So you want to press here the maximal consumption. Yeah. You are not obliged to constrain the function of all the horizon. You can restrict the horizon. And this is in this example, there is this constraint always in. It says that the function f between start time and an end time, here in this case it's fixed, so it's a time window, should always be between a minimal 8 and a maximal 8. Okay? So this kind of constrains the value of the function over a time window. Okay? You can do even better. You can constrain the function over a variable time interval. You don't know the time of this interval is a decision, but you want to constrain the function over this. So this say, okay, if x is present, x maybe is an interval that has nothing to do with the definition of the function. It does not contribute to the function, but it's a condition. You want to express a condition. If you all know planning very well, so this is completely equivalent to condition on an action. Okay, everywhere during an action you have express a condition, and here the condition is that this function should always be between min and max. Okay. Okay. So when you have this, it's also very easy to model another classical scheduling problem, which is the resource constraint project scheduling problem. And again, this is here the complete model, the complete CP Optimizer model. What you do, so in the RCPSP you have a set of activities, you have a precedence constraint network, you have a set of resources, cumulative resources, and each activity requires a given quantity of resource. Okay? And you don't want to exceed the capacity of resource at every time point in the horizon. So you define your set of tasks as interval variables here. You know the size, it's the processing time, it is known in this simple version of the problem. For each resource, you will define a cumul function that represents the cumulated usage of the resource over time. Okay? What is it? It's just the sum of, for each task that requires a given quantity of the resource that is not zero, pulse, okay, of the interval variable and the quantity. So you sum up the variable. And then what you do, okay, in the simple version of the problem, you just minimize the max span. We have already seen that. And then what you do, for each resource, you say that the level of this resource, this cumul function, is always lower than the capacity. This is a given integer. Okay? And you have your precedence constraint network modeled as n before start constraints. Okay? It's that simple. It's simple. Well, again, little parenthesis on the performances. Again, in the same paper I mentioned of 2015, also we were able to, with this model, to improve some lower bound, and maybe, I don't remember, just to close also, no, to improve also some upper bound on very famous instances. Not really realistic again because they're very small. It's 100 up to 100 activities, and it's again also makes span minimization, but okay, it shows at least that on some very academical benchmarks, CP Optimizer is quite good. Okay, this is a little more tricky piece of model that illustrate a little bit the kind of things you can do with cumul functions. I don't know if just reading the model you can understand what it does, but you have basically two sets of interval variables, A and W. You have two cumul functions, and you have a set of constants. What it says is that, it says this. Suppose that you have a set of activities that, I don't know, execute. They do something. What you would like to do is to capture in your model a set of interval, a set of time windows where the resource is used by some activity. Okay? So for instance, this is working, let's say this is working intervals of the resource. For instance here, W1 represents this interval where the resource is used by some activities. And then as the resource is not used anymore for a while, okay, this is no more working time, okay? And you will start another interval of time where the resource is used again by the activities. So, back to the model. What you can say is you have these two things, or two cumul functions, FA, FW. FA is the sum of each activity contribute with a pulse of 8.1. This will count the number of activities executing at each time point, okay? And for F1, the same. You will have a cumul function that is 1 if there is working interval, or 0. These working intervals here, W, I don't know if you pay attention, but you recognize the pattern I explained right at the beginning, this optional chain, because you do not know how many intervals, working intervals you will have, because it depends how you schedule the activities, the red activities here. But you know that, okay, you consider only the first one to be present, and then you will post some always-in constraint saying that, okay, during an interval AI here, so this is the activities, you want that the working activity is always 1, okay? It cannot be 0. You don't want that. If you have an activity working, the green cumul function, you don't want it to be 0. You want that a working activity is executed. And here, for each of these working intervals, you want that if you are in a working interval, then there is at least one activity executing, okay, at this time. So this model is this kind of thing. And then after, of course, this is not a scheduling problem in itself. This is just a pattern that you may reuse, for instance, because suppose okay, your resource is such that it cannot work more than 10 hours. Then it needs to take a rest. Okay, then you can have a maximal duration of this on these intervals. Okay, and you're done. Let's say, okay, you will have groups of activities here working, but then after 10 hours, hop, the resource must be necessary. Stop for a while and continue. This is an example. You also have integral expression to get the contribution of a variable on the interval variable on the cumul function, and this can be used to control the 8. Okay, if you are using a variable quantity of resource, you can use this expression after to constrain this variable quantity. Typical use case if when you are the quantity of resource is related to the duration of the activity. If you are using more resource, the duration will be lower. Okay, so you will have a constraint between this 8 here and the duration of the activity, and you will get this 8 with this type of expression. So to summarize, we have some cumul function expression. You can build cumul function expression. They are expression because when they depend on interval variables, but when you have fixed all the interval variables, the function is fixed. The function is null. And you have constraint on this cumul function and expression on this cumul function. Okay. And you have seen that it's used especially to model cumulative resources, in fact. Okay. I'll speed up a little bit because probably we want to see other things than just the model. The last thing of the model, and then this is the last concept in the model, is the one of state function. I will go very fast for it, but the idea here is that it's a new decision variable, new type of decision variable. It's a state function. It represents the time evolution of a given value that may correspond to the state, the configuration of a resource, and that can be changed or required by interval variables. And the idea is that if you have two interval variables that require incompatible states on this function, they cannot be executed at the same time. They cannot overlap. And also we have some way to say that two interval variables requiring the same state, under some conditions they can be batched together. They start and end at the same time. So you can see the value of the state function as something like in a dynamic system as a state variable describing the state of the time of the system. Okay, and the value is the value of the solution or in the schedule you have computed. Okay, I need to go very fast on this. The idea is that you define just a state function in this way. You can define it with some transition matrix. It means that for switching to one state to another, you also will have some transition time. And then basically what you have is some constraint on the state function. You say that the state function during an interval variable must be always equal to a given value, for instance. And what I wanted to say here is that especially you can say, okay, at the solution, the value of a state function is a set of segments with values. You have the notion of alignment here that say, okay, this interval variable, if you say it's start align, it means that it starts exactly at the time of the segment of the function, of the segment of its function. The fact is that you can use this to build batches, because you can say that two interval variables, if they require the same state, but they are aligned on the start and the end, necessarily, if they overlap at some point, they will have to start and end at the same time, and it will make a batch, okay, on the machine. So, and you have in this way a set of a few constraints on the state function. I won't describe this in detail. This is a simplified semiconductor manufacturing machine, almost the problem we have seen at the beginning, the introductory problem. Here it's a little bit simplified, just to say that, okay, here you have a single machine. You can define a state function that represents the batches on the machine, and you have a cumul function that represents the load on the machine. Here the number of wafers, if you remember the initial problem. What you will do is that the cumul function is, okay, a sum of pulse. Each operation on the machine will pulse with the number of wafers. You want to compute, you have a maximal number of wafers at each time point that can be in the machine. So this will account for the maximal capacity of the machine. And in order to make the batch, you will say exactly what I was saying before, that on the state function batch that represents the different state of the machine, the different families of operations performed by the machine, and you will say that each operation requires the batch to be of the right family, okay, and then it will be synchronized on the start and the end. So two activities that overlap on this state function must belong to the same family and will start and end at the same time. Okay. So again, if we summarize on state function, we have this notion of state function variable and a set of constraints on state function. I've gone very fast for state function, but now we are done. We have seen everything that's in CP Optimizer. Maybe for you it appears a lot. I really can tell you that when you have look at this and you get used to it, it's very, very few. It's nothing to compare to 300 global constraints in CP systems or whatever. So to summarize what we have seen the notion of constant function used to express earliness, tardiness cost, resource calendars. We have seen, of course, the notion of interval variables. That is very useful to express optional activities, over-constrained problems, because you can decide whether or not to execute an activity. Cumul function are used to model cumulative resources, inventories, because you can produce and consume. You can have step at end minus step at start. This state function that you can use to model batches, activities incompatibilities. Of course, sequence variables to model unary resource with setup time, setup costs, and all the possible way to aggregate the individual costs. Okay, so we have covered everything, and this is quite exhaustive. Now, what we can do, and this was supposed to be the second part, so you see, where I'm running quite late, but we won't maybe do everything, and then maybe it's a bit up to you what you would prefer to see. So I have a few examples, just complete example. We have already seen job shop scheduling, we have seen resource constraint project scheduling, simple versions. I can talk about performance in general. I can talk about how you solve a problem. This is very fast because the main thing is that you press a button and solve. Okay? But there are ways, there are parameters to tune the search a little bit. Things you can do quite easily to speed up the resolution. There is a number of tools around CP Optimizer. If you are used to CPLEX, maybe you know there is a conflict refiner in CPLEX that can help you if your model is infeasible to explain why it is infeasible. We have heard about explainable planning. This is about explainable scheduling. And there is also something that go a bit over what happened under the hood and how it works when you press the solve button. We can treat several of them because it's quite short. Each of them is not very long, but.
Tools.
Huh?
For me, tools.
I would be interested in knowing how bad modeling may affect the solving procedure behind the scenes.
Okay, sure. Okay, yeah. Okay. So because I promised it in the beginning, I will show you one example. It is one of the introductory problem, but I will go very fast. Then I can talk a bit about what's good and bad in the modeling, because as you guessed, you can do bad model and good models with CPO, as with MIP, no problem. Then the tools we have, and then under the hood some lenses. Well, that's almost everything. So I will jump very quick to the. Yes, I wanted to say that tomorrow at the conference I will present another example, which is a satellite observation scheduling problem, which is a problem submitted by NASA at ICAPS last year, and then we have some new results with a CP Optimizer model. But again, a very small CP Optimizer model. So I will quickly jump to this semiconductor manufacturing scheduling problem. This is a multi-mode RCPSP, but it's basically very similar to RCPSP actually. You only need to have alternatives for each mode, and each mode is described. You will have the usage of non-renewable resources and the usage of renewable resources as cumul functions. So what I find it quite elegant is that for the two types of resources, we are completely different here in this problem. You have the same type of model and you use the same concept. You have one expression for non-renewable resources and one expression, cumul function, for renewable resources, and you write exactly the same type of constraints here in the model. And this is very compact. Okay, we are efficient on this type of problems too. For instance, we had CP Optimizer 2 years ago, the industrial modeling competition, which was a kind of multimodal CPSP, actually a simpler case of multimodal CPSP. Okay, this is. Oh, maybe I show this. Okay, this is a model, complete model. I won't describe the model itself, but for the satellite communication scheduling problem. But this is the same model in OPL. Okay, you recognize maybe the OPL. This is the same one in C++. It's a bit longer. Okay, because you need to define, but it's the same concept, the same notions. And this is the same one in Python. Okay, it is shorter. Sometimes Python models, sometimes are even shorter than OPL ones. Because you can do smart things. Sometimes here it's a bit longer, but okay. So you remember the introductory problem? Okay. Okay. These are the same slide describing the problem, but here is a complete model for it. I'm sorry, it's very small, but I had to make it fit on the slide. But just even the 1/3 of the problem is just data reading, so the model itself is here. Okay. And what we do is that we have an interval variable for each lot. Okay, that represents the spanning time of the lot. We have one interval variable for each step. As the step can go on different alternative machines, we have an optional interval variables, which represent the possible association of a step to a machine. Okay, the possible allocation of a step to a machine. Well, additionally, here we have an integer variable. I didn't say it, but of course, in CP Optimizer, we also have integer variables and more classical CP things, and you can mix together. And then this is a lexicographical objective. So we have also the possibility to represent a static lexicographical objective here, where you have two expressions. The first one is the higher level criterion, and the second one is okay. Here you would model the time lag violation. You recognize here some square expressions. You remember the shape of the time lag violation. We have some square function at some point. This is just description of the expression. This is a weighted tardiness. Okay, so this is a weight, and this is a max between the end time of the lot minus the deadline. Okay, and 0. So if you're running after the deadline, then you have some price to pay. So, and then you have a set of constraints. For each lot, you say that it spans all the steps of the lot. Okay.
Sorry, what objective optimization is limited to 2 objectives?
No. You can have an array of objective executions. You have precedence constraints between the steps belonging to a lot. You have here this time lag. You have also some precedence constraint. We model them with an end at start constraint with a delay that corresponds to the lag. Okay, and this lag is used in the expression here in the cost. And then, well, you have the alternative that say, okay, a given step must be executed by one of the possible machines. Okay, and then you have the constraint we have seen a little bit before for the batching machine. So the batch is always used with this always equal constraint on the state function, and then the cumul function, okay, that represents the maximal number of wafers that you can execute simultaneously on the machine. That's all. And it works very well. There was a paper recently with some people. For instance, the first author 1 year ago was not, or 1 year and a half ago was not absolutely, did not know anything about CP. He was used to work only with MIP for scheduling problem. And then he discovered CP. He discovered CP Optimizer. And now he's a big fan of CP Optimizer and use it for everything. For scheduling, and in particular he has rewritten and retried some old paper he had published on some benchmark and found that CP Optimizer much better than the MIP models he used to use. And this is the conclusion of one of his papers. I can go through, but okay. Says that what's nice in CP is the natural formulation of the problem, which is close to the description of what you have. It's very concise, flexible, scalable. Unlike meta-heuristics, you have no such right because the resolution is for, okay, you just solve. And he found out that it was much better than the MIP model he had written before. Okay, but it's a good summary of the main interest of CP Optimizer in the context of scheduling. So, yes, if you have a scheduling problem, there are many ways to model it using CP Optimizer. Anyway, there are different ways to model it with CP Optimizer. And of course, not all of them are equivalent. So if you're used to MIP, you know that it's the same with MIP. It's good to know some tricks, some things to avoid, and so on in the models. For CP Optimizer, it's also the same. So there is a few, let's say, best practice or things that should guide you to write efficient models. They all follow two meta advices, I would say. The first thing is that you should try to factorize everything that can get factorized in the model. This is a bit generic as a way to state it, but we can see some example. And the second one is to exploit the power of the scheduling concepts, and especially the notion of optionality of interval variables to find a nice model. Example. So one thing is that a measure of the complexity of the model is the number of variables, of course, the number of groups of variables with different semantics, okay, because it maybe means that you have different sources of complexity in the problem, and sometimes it's harder to treat. The number of variable types, if you are using only interval variable, or if you mix integer variable with interval variables. Ideally, if you can have a model with few decision variables, few type of different variables with different semantics, and if you, for example, can avoid having mixing integer and interval variables. Yes, those are general things that that you can use as guidelines. One thing that, for instance, in particular, if you are in a scheduling model and you want to start to create one decision variable for each time point in the schedule, that's a bad idea. Okay, but maybe if you're used to MIP, maybe people have tendency to do this kind of thing, to discretize, to do things. No, if possible, not, because the main point of CP Optimizer and the concept is to use functions of time and never to discretize time. Okay, so if you start to discretize time, you should try to think other ways of modeling the problem.
But we discussed there are some problems for which it's going to be difficult, right?
Oh yes, yes. CP Optimizer. No. Yeah. Sure. And so there are two things. You can discretize time, and this is very bad. But sometimes, because you have a complex activity, you can discretize the activity, cut the activities in little pieces. For instance, because if you notice, the function and cumulative functions are not continuous, they are not linear, they are stepwise. So if you want to model something continuous, for instance, you can split an activity into more interval variables, and they're constrained to end at the start of each other. This can be good. This can be good. If you can completely avoid this, it's even better. But sometimes, this is only advice, because sometimes there is no way to work around this, for sure. So of course, the idea is to exploit again this notion of timelines in general, sequence variable, cumulative function, and state function to model the problem. Of course, another sort of model complexity is the number of constraints. So in general, a good indication that you have at least achieved a reasonable CPO model is when the size of the model in terms of number of constraints, number of variables, is linear with the data you have. Okay. In MIP, it's quite often not possible to have this, because if you have an activity, you have always n square and cubic constraints variable, because you have no way to model it in different ways. In CPO, very often in scheduling, you can end up with a model that is linear in terms of the data. And this is, well, I'm not saying it's always possible, it's quite often possible, and it is a good sign that, okay, you have really starting to have a nice CP optimizer model. An illustration of this is that if you have activities that under some conditions they cannot overlap, but the condition is not as easy as just this is not an overlap, for instance, a global overlap, but you can try to find smart things exploiting state variables, cumul function to express this in quite a compact way. Another thing, very general guideline, and very important, is, if possible, to try to avoid using composite constraint, or sometimes in CP called meta constraints. It's constraint on constraints. Example. Suppose that you want to write this. Okay, if I have an interval variable A, an activity, let's say, and I want to have an expression. If the interval is present, I want to say that it is the end of the time. If it is absent, it's a constant k. Of course, maybe you want to write this. This is correct, but you can write it in a much more compact and more efficient way. Okay, this is just okay. The end of a and k if it is absent. This is a very, maybe a bit stupid example, but I know that people tend to write this kind of thing because maybe sometimes it's more natural. Okay, look this. If you want to say that if A is present, then it starts after 10. It may appear quite natural to write this. Presence of A implies it's much better to write this. Okay? If A is present, it will start after 10. If it is absent, the value of the expression is 10 and the constraint is satisfied. Remember the thing I said, try to factorize as much as possible. In CP, what's bad in CP if when you have a constraint or an expression where the same variables appear several times in the expression. Okay? Here you see it appears 2 times, here even 3 times. Just one thing is if it can appear only 1 time, it's best. The idea is to think of factorizing. There is one big, so I say avoiding this type of meta constraints. There is one big exception, and I talked about it earlier, is this binary logical constraint. This you can put them and no problem. I mean, they're treated, they're optimized, and they're so. Actually, if you are using the constraints that I described in this presentation for scheduling, actually we do not allow to have this constraint in composite constraint, except for presence of. You cannot have them in meta constraints. You cannot say, you cannot write, I don't know, presence of X implies no overlap, and then something. It's on purpose, because we could have done this. We could have allowed this, but it means for sure that there is a better way to model it. So avoiding composite constraint. Maybe this is the main advice. Well, this is again same kind of thing. If you're tempted to write things like, okay, I have an integer variable that distinguishes 3 cases. If x is equal to 1, then I don't know. Yes, the length of the interval is 10, and then it consumes given quantity of resource. If it's 2, then it's this. It's kind of a multimode, you see. No, this is very bad. If you have multimode, it means that you have alternative things. You should create optional interval variables, 1 for each case, okay, and then post an alternative constraint in this case, and then, okay. So, yes, so one general advice illustrated here is that it's very good to capture all the, if possible, it's not always possible, all the non-temporal decisions by Boolean constraint on the Boolean presence of interval variables. Okay, so some kind of modeling advices. I don't know if this answer a bit job questions, but what we wanted to talk. Tools, yes, tools. No, properties of the search. Oh, I need this because. So, the search, the automatic search is complete. Okay? So, if the problem has a solution, it will find a solution, prove optimality, but okay. You may have to wait for ages before it prove optimality, for sure. If the scheduling problem are very challenging for optimality proof. We have seen on job shops that we're not too bad. We're much better than MIP. But still, I mean, if the size increases, for sure it's right. The search is anytime, okay? So, it means that it will first produce a solution and then improve the solution. So, of course, it may take time to produce the first solution. Usually it's quite fast. Why? Because it's a property, I think it's a fundamental property of scheduling, is that finding a feasible solution in many scheduling problems is quite easy, very easy. Because there is always a possibility to do nothing in scheduling. The world won't stop. You do nothing. It's a very bad solution, but quite often it's a feasible solution. So I exaggerate, but this is to say that, yes, finding a first feasible solution is usually very easy, and then the search will improve. The search we exploit parallelism, okay? So the search is parallel, unless you say otherwise that you want to use only one thread on your machine, but the search is parallel. One important thing to know is that it's randomized. It means that internally in the search, so here I'm starting to go a bit in the under the hood section, the search is randomized, so it uses some random generator to break some ties, okay? And the seed of the random generator that is used in the search is a parameter, so you can change it if you want. Why there is a seed? Because the search is, in spite that it is randomized, it's deterministic. So if you solve twice the same problem on the same machine, okay, even if you're using multiple worker and parallelism, it will always produce the same solution in the end. So usually if you have a complex problem, you put a time limit and then it will return with the best solution found so far, and it will be the same. Okay. This is very important because, especially if you're working in the industry, the customers, they don't want to run the same problem twice and have different solution. No, they don't accept. And of course, it's good for debugging also. Okay, so this is yeah, maybe one thing I should say is that, so we have seen a few numbers, we have even not seen all of them, but some problems. Internally, at IBM, we have a set of scheduling benchmarks. Currently it's 137 different scheduling problems, okay? So one of them is job shop, for instance. One of them is this semiconductor manufacturing problems. So this is different families of scheduling problems. And for each families, okay, we have a set of instances. And what we use this for is to measure how much we improve from version to version. We improve automatic search, just like CPLEX does, for instance. And while you're using this kind of quite big scheduling benchmark for assessing the performances. So we have collected this benchmark from different sources, of course, classical problems. So we try to spend time looking at the academic papers that are published, and sometime when we find time, we try to model the problem and then add it in our benchmarks. Of course, we have problems coming from the industrial problems we are working on. They come from customers, business partners, and users. We have an optimization forum, I will say a little bit after, and then some people discuss sometimes some problems and it gives us some idea to generate new problems. The size of this problem is quite diverse. There are very small problems. The small is only 30 interval variables, 30 activities. The larger is 1 million. Different type of resource, objective function. So, of course, on this large problem, we cannot always find the optimal solution. So, yes, I just wanted to say a few words how we evaluate the performance. So, what we do is we give a time limit, okay, and then we look at how the search converge to good solution. And then what we are used to give when you have, okay, when we release a new version, for instance, 1 month ago we released the latest version, 12.7.1, And we say, okay, it's on scheduling problem is 40% faster than the previous version. So what does it mean faster? What we do is when we have two versions of the CP Optimizer or two versions of the search, we try to compare this. We try to compute the speed up ratio in terms of time, and roughly, when the description, it estimates how much faster the best algorithm, say A, find a solution that is equivalent to the best solution found by the worst one. Okay, and we can to average this. I show an example here. This is a real example. This is really one instance in our benchmark. Okay, this is a job shop with academical problem, job shop with earliness tardiness. We run this on several random seeds. Okay, so here this is average convergence on this instance for this is time, this is objective. Okay, and this is I didn't choose this example very innocently because it really exhibits that the new version is faster than the old one. Okay, I must be honest. But this is to illustrate the fact. And this is, you see, the convergence. So for instance here, the worst version is 12.7. It more or less finds this solution, the best solution. And then with 12.71, okay, we find the solution, okay, at this time. So it's about, I don't know, 30, 40 times speed up. This is how we evaluate the speed up. And yes, this is kind of, just to say that we're making progress, we're continuously making progress on the automatic search. This is the years and the version. I started in 2011, and the reference is version 12.2, and from version to version, you see that this is the speed up. Okay, so the last version, since December, we see we have about twice faster in average. But this is an average. If you go, because what interests the people is not what the average, it's how it behaves on their problem. Okay, and it's quite interesting. For instance, there is also a problem where you see flow shop with earliness tardiness cost. I didn't describe this model, but we are about 300 times faster. Okay, multimodal CPSP, it's 8-9 times faster than we used to be, and so on. The tools. Yes, the tools. Yeah, this is when you're working in the industry. This is one thing that you could think of when you're building an optimization engine for an application. This is not related with scheduling. This is general. You could say you start from a formal definition of the problem. You design an optimization model. You have some data. You run it, and then you evaluate your problem. This is nice, but this is not the way it works. Because for industrial projects, you start from a very informal definition of the problem. The user, the customer, does not really, even sometimes he has an idea what he wants to optimize, but how? It's not formalized, it's not formal, you start from words. Okay? Finding and agreeing on a formal definition of the problem is something that is not easy. Then, okay, you will have to design an optimization model. But the other source of problem is the data, okay? Because the data is never in the way that when you are working on some benchmark, you have the data, you have the formal description of the problem. It doesn't work that way, of course. So you have data, you have some missing data, you have some wrong data, etc. Where I want to go with this, because you probably are all aware of this fact, it is that when you design a model, it's always very, very interactive and iterative process. Okay? You, without stop, change the model, try to do something, find a solution, show the solution to the customer, say, no, I don't like this, what happens? There is problem in the data, you have a model, it's infeasible, things like that. Okay? So there are a typical number of questions that arise during model design, and it's always the same ones. This is not related to scheduling, but in scheduling is a particular case of this. Typical question. I have a model, it's quite complex, I've written, I don't know, in C++. The code is, I've code a bit everywhere to create my model. In the end, on a given instance, how does my model look like? What kind of constraints I have on this instance, how it looks like. Second question, maybe does it constrain some weird things I'm not aware of because the model is so complex? What's inside? It's related to the first question. Quite often also, when you solve a problem on an instance, it will say it's invisible because you may have bugs in the model, you always have problems with the data that is not as you expected, there are some missing data, whatever. So, from experience, 90% of the model I try in an instance, in the beginning, they are invisible. So, you need to explain why the model is invisible and try to find out what's the problem. Another question, of course, is why it's difficult to find even a feasible solution. Not an optimal solution, but a feasible solution. Other type of question, I have two variants of my model, and this is a very important question. I have two variants, I'm working on the model, I'm trying to improve it. I have two versions of the model. Which one is better than the other one?
It happens with students quite a lot. They don't understand why, making this change is better.
It happens to the students, it happens to us. It happens to everyone. Yeah. And the way to assess two versions, and the answer is not that easy, because especially when, it just may be by luck, because you have added something that changes something in the search, you follow a different path, and then you find a better solution. It's not easy. Okay. Another type of question is maybe some customer wants some advice from some CP Optimizer experts. So with this, we kind of have a convergence with CPLEX, because CPLEX already, it's a field optimization field which is much more mature than CP Optimizer when working on industrial problems. So they have developed a set of tools around the engine. And then what we have been doing is doing the same kind of tools for CP Optimizer. So first we have an input-output file format for the model, for your instances. You can dump them. Second thing, and I will firstly go through this thing, we have this notion of a bit modeling assistance. We have some model warnings. Okay, there is a search log, of course, like for CPLEX, that can give interesting information about what happens during the search. Conflict refiner, this is when your model is invisible, and then interactive executable. So we have an input-output format. This is a format that is human readable, so you can dump your instance of problem and your model in a file, and it makes it very easy to understand what's inside your model actually. And this you can dump. We have a format that we call .cpo format. You can also communicate this model, this instance of problem, to some experts, some IBM, some partners, to say, okay, or maybe there is a bug in CPU, and then you want, okay, there is a problem with this model. So it's useful for communication and also for understanding what's inside the model. So it's human readable, yes, you can export it. This is an example. I'm not sure you can read it easily, but and it has some information also about the lines that generated the model. For instance, here, this is a flowchart with ordinate tardiness written in Python. And when you dump this instance, okay, it's human readable. You see these interval variables here. You see this objective function. It's a minimize, you see. And it says which line in your code has posted this constraint or has posted this objective function. Okay. So, and it shows also here the parameters, search parameters. We didn't talk about it, but here time limit 10, for instance. And so this is very useful. When you have this, you can have a look and say, okay, what are the constraints in my model? Okay. So there is also the notion of warnings. You can see CP Optimizer as when it runs, just a bit like a compiler. It will analyze the model and say, okay, there are strange things here. Maybe it's not a problem at all, but okay, this way you are aware of maybe some things that you didn't expect to be in the model, and then can help you do something. For instance, this is okay. We have here an interval variable x that is not used in the model, that is not used in any constraints. Why not? But maybe you didn't expect. Maybe you forgot to add a constraint in this. Okay, and there is a bunch of different warnings you can get from CP Optimizer. Okay, the another important tool for that is the search log, because it can give you information about what happens during the search. So you have problem characteristics. If you change some parameters here, you see that you have the modified value. For instance, you specified that you want to use 2 parallel workers with time limit of 30. Information about the root node. Then during the search, when it processes, information about the new solutions that are found with a cost here, the objective. So we'll see how it improves. You have some periodical information on the search, and then in the end you have some final information. Here it says, okay, it did not find proof optimality, but it says the search is terminated by limit. Okay. Another important thing is the conflict refiner. As I said, quite often the model is infeasible, and we want to find an explanation why the model is infeasible. And I said explainable scheduling because I think that most of the questions a user can have also on a solution, saying, for instance, I don't know, why didn't you schedule this activity, or why did you select this machine for this activity? This also boils down to conflict refiner, because you always can say, okay, you would find a variant of the problem where you are the constraint that the machine should not be allocated to this activity. This is pretty easy to do in the model, and you are the constraint. Probably the explanation will be that, okay, either the problem is infeasible or it makes the cost worse. Okay, so you are the constraint on the cost, and at least in theory, the explanation, if this model is feasible, the explanation will be, okay, I didn't consider this possibility, but yes, it's possible, okay. But if the model is infeasible, it will tell you. So let's back to the conflict refiner. The problem, the objective of the conflict refiner is to, from an infeasible model, select a much smaller, usually much smaller subset of constraints that is infeasible by itself. Okay, and this is usually very useful to. This is really an explanation that you would expect. So in this case, for instance, if you would say, okay, you force in the model to allocate on a different machines, and you force not to degrade the cost, then it could say, okay, it's because you have this and this and this and this precedence, and then this will push the activities and the cost will be worse. Okay. I have an example on this. This is an example we have not seen, but this is a satellite communication problem. The one that I have shown under the different API in Python, OPL, and so on. This is another constraint problem where all the intervals are optional here. You see, you want to schedule as much tasks as possible. And an interesting question is, why is it over constraint? What happens if I try to schedule all the tasks at the same time in the schedule? And then you can run the conflict refiner on this, and then on this instance of problem, it will just exhibit a small set of constraints, 4 or 5 constraints, saying, okay, if you select, because you have some narrow time windows here on the resource, okay, and then you have not enough capacity on the resource to execute these 4 tasks, okay. This is just one instance of infeasibility in the problem, but one is enough to explain why it's infeasible. Conflict refiner, okay. Interactive CP Optimizer, this is just, I wanted to speak about this interactive CP Optimizer, and it's in relation with the fact that it's important to carefully evaluate, if you have 2 variants of the model, which one is better than another one. You cannot do that on a single instance with a single run, okay? Otherwise, you will for sure fall into this thing of it's luck, bad luck, etc. So you need to evaluate. You need to have, of course, when you are working on a project, it's much better to have several instances to test on. But sometimes it's difficult to have many instances. But then, even if you have a single instance, you should, when you evaluate the 2 versions of the model, run it with different random seeds and make some statistics. Okay, and in this interactive CP Optimizer, so it's an executable. You can, one of the functionalities for that is you can just read a problem, a CPO files, and run it on different random seeds, and then provide some statistics. Here, again, it's a job shop example. I don't know if You know this instance of JobShop example, FT10, but it has remained open for 25 years. And the question we ask ourselves is, okay, this is the same version of CPU, but is it better to use some search parameter or not for this problem? Here, typically to extend the propagation level of some constraints, okay, to plug some complex propagation algorithm for the no-overlap constraints here. And then you run it on 100 seeds, so 100 different random seeds, provide some statistics here. And then the answer would be, okay, it's even not clear because the standard deviation here is, it seemed to be that the default, when we don't change the parameters, slightly better, but it's not clear. But okay.
Did you have tools that automatically optimize parameters?
Yes. Currently, we have not delivered these tools. We have them, but it exists for CPLEX. For CP Optimizer, we have much less parameters than CPLEX. CPLEX have a huge number of parameters. For CP Optimizer, we have, in practice, 5-6 parameters that are used. So, and quite often, there are 2-3 that you can play with. So, the combinatorial aspect of this is not difficult to address. Last thing, under the hood. Okay. I cannot describe everything that happens in CP Optimizer. That would be more than this tutorial. And yeah, but just some ingredients. Okay, some ingredients, and then I can say a few other. One ingredient is presolve. Presolve in MIP is something very important. Okay, it's you analyze the model and you try to remodel, improve the model, or tighten the model, tighten the formulation a little bit. In CP Optimizer, we do this. We do this. This is an area where we are improving and improving. I give here a very simple example of very simple presolve rules. So when you have extracted the problem, we apply this set of presolve rules to reformulate the problem. But they're very simple, these ones. But okay, if you have a constraint like this, end of x is lower than start of y, then this will be reformulated in n before start. I say that this type of constraints are specific in the problem, so they are very well handled, so it's better to have this formulation. Suppose that you have a constraint that say x and y overlap length is 0. They cannot overlap. And x start before the end of y, then you can strengthen this precedence by saying that x must end before the start of y. It's kind of thing like that. We aggregate some constraints here. If you try to find some cliques, for instance, of different variables to put a global constraint all different. We try also, when we have expression, to do some common sub-expression elimination. Okay, this increases the propagation. We have many rules, and they're applied before solving the problem. Propagation. This is the only thing where people used to CP can switch on the neuron about CP. One of the ingredients is, of course, constraint propagation and research. It's CP. We are doing one thing we are doing inside is CP. I say that we aggregate this constraint in logical network, temporal network, and I can say also a few words about how we propagate this no overlap constraint. But the logical network, so I say it's equivalent to a two-set model. So we aggregate this into an implication graph between literals, or let's say opposites. Okay, and we perform the transitive closure on this. What happens is that it allows to detect infeasibility very easily. So if you say presence of x implies presence of y, and I don't know, presence of x implies not presence of y, then it's infeasible. And it allows also to query in constant time. If you're given two interval variables in the schedule, in constant time you can know if x implies y or x implies not y. What's the status between these two variables? And this is used in the search. We'll see. The precedence network. The precedence network aggregates all the temporal precedence constraints into something like a simple temporal network, but extended with this notion of Boolean presence variable. So you have nodes that represent the start or the end of the interval variables. Arcs represent minimal delay between two nodes. What's important to know is that for each node, so if we maintain the domain, the mean and the max of the value, or for instance of the start time, if, this is something very important, if the interval would be present. So if you have an optional interval, the optionality status has still not been fixed in the search, we maintain this bound if the interval would be present, okay? And the propagation will exploit the logical network. I give an example here. Suppose this problem. You have x, all these intervals are optional. X, you have a precedence constraint between x and y, and you have some implication constraint. Presence of y implies presence of z, and presence of z implies presence of x. When you look at the logical network, we perform transitive closure, so we know in constant time that the presence of y implies the presence of x. What you can do when you propagate here the precedence constraint, you can say that each time you execute, if y is present, then x will necessarily be present too. Okay? So x will push, let's say the mean time will push the mean time of y. Okay? So even if you still don't know if this interval will be present or absent, you still can propagate on the domain, on the conditional domain, if the interval variable would be present. This is something that is quite amazing, because when you have complete optional parts in your schedule, okay, optional, it's able to propagate inside, okay, and this detects some inconsistencies and may so say that some interval will be automatically absent and things like that.
Is this published? Maybe this is well known, I don't know, I'm not a specialist at all.
Yeah, this
STN, but these things with STN plus absence, presence. Is this published? Or
yeah, it's published. It's published in 2008. Okay. So we have seen that the precedence network exploits this logical network, and this is, well, I say this is important because you can propagate even if the precedence is not fixed. So what we have been doing at the beginning of CP Optimizer, this has not changed a lot in that time, is that we have been extending some classical STN propagation algorithm to the case of this type of directional propagation, because when you have implication in the logical graph, you can propagate from one side with the precedence constraints. So, and basically we have two types of algorithm. At the root node, we basically have extended some improved version of Bellman-Fowler algorithm, okay, at the root node, when you propagate is everything once in a row. And during the search, when it is incremental, we adapted and very easily adapted an algorithm from Angelo, which published last year, to automatically detect some loops and infeasibility. And when it is extended to optional interval, it allows to detect some absent interval, because if it would be present, then you have some loop. Okay, this is very nice thing. Yeah. This is something a bit interesting, because, so you see, we aggregate the precedence constraints into a network with specialized algorithm. What you can do is you take a CP, an integer CP system. I took Choco. I took CPO also, because we have CPO integer variables. And then, just on a very simple problem, we have just a chain of n activities, okay? A chain of n activities. And then, if you are modeling it with integer variables, just add a lower than constraint between the start, the variable, integer variables that represent the start and the end of intervals. Okay. I looked at what happens at the root node, the initial propagation of this. Okay. And look, this is the number of activities in the chain, and this is the time it takes to perform initial propagation. Okay. So if you're not doing anything special, you just perform local propagation of these little constraints here. This is terrible. Because what happens is that in the chain it will start to propagate somewhere in the chain, then it will push a little bit, but then it didn't discover that you must push again something, and it is, I don't know what the worst case, but it's at least quadratic for sure. And in CBO, well, it's flat. I mean, nothing. The root node is propagating the temporal network at the root node, even for large problems. It costs nothing. But even such simple thing, if you don't pay attention to the fact that you're solving a scheduling problem, a precedence network, this really pays a lot. Okay, well, I'm almost done. For propagation, we have also for propagating timelines, so in general, I mean no overlap, Preamble function, state function, we are using timetabling algorithm, okay, which maintain, the idea is to maintain a set of cells where you have minimal and maximal level on the resource. Okay, and then, and the default propagation, yes, we are using for that is timetable algorithm. And then I also did recently some comparison from very state-of-the-art propagation on timetabling algorithm, and you see that CP Optimizer, this one is really behaving quite honestly, quite good compared to the time. This is the time now. This is the time for and the size of the problem. So it's faster. It's difficult to compare because CP Optimizer is optimized, it's C++, sometimes here it's Java. So I'm not saying it's better, but I'm saying it's very good. Okay, but we have more complex propagation in the engine that require more time, but that we use that automatic search decide when to use or not some propagation. Okay, so in our team we have Petr Willem, who is a big specialist of edge finding algorithm and so on, and he has implemented this algorithm, and they are very useful, especially for small, medium-sized problems for proving optimality. Okay. Yeah. So the time is over. If you have a couple of minutes, I can describe more how these basic elements of propagation are put together to provide some good results. I'm basically done now, so just.
Does the pre-solve deal with things like partitioning and decomposition of the system if you have disconnected timelines?
Yes.
Parts of the graph?
So no, currently no. Currently no. This is something we probably will do at some point. Now for scheduling, this seldom happens because you always have connections through the resources. But yes, and more generally for CP, yes. Currently we do not do that, but this is kind of things we want to do.
My other quick user question is: does iLog or IBM, do they have even a simple generic Gantt facility for visualizing, pulling in data from the results, or just to be able
So yes, CPLEX Optimization Studio is also used. There is also something a bit larger around it for helping developing applications, and when you have some stuff about visualizations. Yes. Okay. So when you are pressing the solve button, actually there are two different search that run concurrently. Okay. It's a large neighborhood search. The objective here is to quickly produce good quality solution and to improve on the solution. And basically it starts from a solution and then perform some local search or large neighborhood search to try to locally improve the solution and then find better solution. This was published in this paper, and this is not exactly what's inside CPO because you see this paper is old, but it gives a good idea of what happens. And more recently we have this failure-directed search, which is a complete search, and this search is switched on automatically when the system thinks that okay, now we have difficulties to find better solutions. There are chances that we are the optimal solution, and we'll try to spend some effort proving that you cannot do better. And so this failure-directed search is, as the name says, directed to fail. It tries to prove that the model is infeasible. This is the automatic search. Now, if sometimes we have a completely different type of search, you can switch to a parameter. This is not by default, but sometimes it works quite good, which is based on genetic algorithm. Okay, so we can have a very general genetic algorithm on top of the CP Optimizer model, and well, sometimes it's better than the default search. Sometimes, so this is one of the parameters that we're trying. Okay, now after I have details about large neighborhood search and the failure-directed search. Yeah, another ingredient that is very useful is the temporal linear relaxation. So this is one. So when you are minimizing make span, this is called so-called regular objective in scheduling. The idea is that you will always have an optimal solution where the activities are as early as possible on the left. Often the objectives are not regular. Often, if you have some earliness, for instance, you want to push some activity, it's better to delay some activities. Okay? So, especially for this type of problems, what CP Optimizer automatically is using is an LP relaxation of the problem. So just like in MIP is using LP relaxation quite heavily, in CP Optimizer sometimes we use an LP relaxation automatically. The use is less intensive than in MIP, but we use it to guide. So this is a relaxation. We solve a relaxation of the problem at each moves of a large neighborhood search, and we use the result of this relaxation first. It can at the root node provide some lower bound, interesting, sometimes yes, sometimes not, but mostly we use this to guide the search because it produces the kind of good placement for the activities, okay, and then the search try to place the activities close to these values. So this is one of the very useful ingredients in this search. Okay. One last thing is that if you're a big fan of CP, probably you like to write your own constraints or your own search. This is something we have completely abandoned to do for industrial project because the rest is completely much better and you get much better results much faster. Now, for researchers that like to investigate new constraints, new type of model, this is, and we will support this for very long. This is completely possible, but this is only possible in C++. Okay, so you can easily define, you can change the engine with your own engine. Okay, and use easily your own constraint, your own propagation algorithm, and your own search. So I'm finished. I don't know if I have convinced you that it's easy to try and that if it's easy to learn, but to learn we have covered everything. So it was a bit dense in the first part, especially I guess, but there is no additional concept in CPU. It's much more than in linear programming when you have only linear constraints, and for sure. But that's it. Okay, if you're interested by CP Optimizer, so if you have CPLEX, you have CP Optimizer, so there is no question. You can download it if you are a researcher or teacher freely. And if you have questions on CP Optimizer, once you start to use it, there are some CP Optimizer forums. If you're using CPLEX, you know that there is a forum for math programming. There are some forums for CP programming. They are quite active. There you can ask any questions. You can get support from us because we always make sure that each question that is asked there is answered, either by us or by someone else. You see that I even participate to this. So that's it. If you have questions, final questions. Okay. Anyway, so
is it possible to get slides today?
yes, sure. They will be posted somewhere on the site of the conference, I'm sure. And if not, then ask me. I'll send them. Sure. And yes, and tomorrow at the conference, I will present one of these models. And this is a very interesting use case where the problem doesn't look very complex, and where apparently it looks quite, the problem looks quite tricky, but we could manage to have a CP Optimizer model that follows this kind of rules where you, and for having good models, and it performs really good. I don't know. Thank you.
Thank you.